Imagine a world where everything you see, touch, and even breathe is composed of tiny, visible building blocks, each one a marvel of nature's design. This world is not a figment of imagination. It is the reality of our universe, where atoms reign supreme as the fundamental units of matter. From the soft pillow cradling your head at night to the vibrant colors of your favorite tea mug, every object around you is a complex arrangement of these minuscule particles. You, too, are a walking, talking assembly of atoms. A living testament to the intricate dance of chemistry that unfolds in every moment of existence. At first glance, atoms may seem simple, yet they are anything but mundane. Each atom is a universe unto itself, composed of a nucleus at its core, surrounded by a cloud of electrons that dart about like energetic fireflies. The nucleus, dense and compact, houses protons and neutrons, the very essence of what defines an element. Protons, with their positive charge, determine the identity of the atom, while neutrons, neutral in charge, provide stability, holding the nucleus together against the repulsive forces of the protons. As we embark on this journey through the world of chemistry, we will uncover the secrets of these tiny particles and the remarkable ways they interact. We will explore how atoms bond to form molecules, creating the vast array of substances that make up our world. We will delve into the forces that govern their behavior, the energy that drives their reactions, and the delicate balance that sustains life itself. So, settle in and prepare to be captivated by the wonders of chemistry. Where the smallest components of the universe hold the key to understanding everything around us. For as long as humans have gazed at the stars or marveled at the complexity of life, one question has persisted: what is everything made of? The answer lies not in grand celestial bodies or mystical forces, but in something far smaller, quieter, yet infinitely more profound: atoms. These unseen architects are the silent storytellers of the universe, weaving together everything from the shimmering screen before your eyes to the very cells that compose your body. You, reading these words right now, are a temporary arrangement of these ancient particles borrowed from stardust, shaped by time, and held together by invisible bonds. The idea that matter is composed of indivisible units stretches back millennia, whispered by ancient Greek philosophers. Yet it took centuries of science to reveal the truth. Today, we know that atoms are not the ultimate smallest particles, far from it, but they remain the essential foundation upon which all chemistry, all biology, and all material existence are built. Each atom is a delicate balance of forces, a nucleus crammed with protons and neutrons orbited by elusive electrons. The protons, positively charged, define the atom's identity. Single proton makes hydrogen. 6 protons create carbon. 8 protons forge oxygen. Change the number, and you change the element itself, altering the very fabric of reality in subtle but consequential ways. What is astonishing is how much emptiness resides within atoms. If the nucleus were the size of a blueberry, the nearest electrons would swirl somewhere near the edge of a football field. This means that everything solid around your skin, the chair beneath you, the pages of a book is mostly empty space. The illusion of solidity arises not from densely packed matter, but from the relentless interactions of these ghostly particles, repelling and attracting one another in an unending cosmic dance. Yet, within this phantom landscape, atoms hold immense power. Their behavior governs the texture of silk, the sharpness of a diamond, the liquidity of water, and the combustibility of wood. Carbon atoms, with their unparalleled ability to bond in long chains, form the backbone of life itself, DNA. Proteins, the glucose fueling your thoughts at this very moment. Iron atoms, forged in the hearts of dying stars, course through your veins, carrying breath to your cells. None of these atoms are aware of their role, yet They shape existence with silent, unerring precision. Delving deeper, we uncover a universe of simplicity and wonder. A single grain of sand contains more atoms than there are stars in the observable universe, each one identical in their basic structure, yet capable of infinite variety. The periodic table is not just a chart, it is a testament to how finite ingredients create boundless complexity. The same carbon that blackens a charred piece of toast also gleams in a diamond, its fate decided only by the arrangement of its atoms. If atoms are the alphabet, then chemistry is the poetry that composed the interactions that transform solitary particles into molecules, and molecules into everything we know. Bonds form not out of desire, but necessity, as atoms seek the lowest energy state, the most stable configuration. Sometimes they share electrons in covalent embraces. Other times, they trade them outright in ionic transactions. Occasionally, as in metals, they pool their electrons like a communal treasury, enabling conductivity, malleability, and the luster of gold. We stand today at the precipice of understanding. The air you exhale, rich with carbon dioxide, will be scavenged by plants, its atoms repurposed into leaves, stems, and fruit. The oxygen you inhale was once liberated by tiny green algae, a gift from ancient photosynthesis. Your body is not a static entity, but a whirlwind of chemical activity, cells breaking down sugars, neurons firing electrical impulses, enzymes meticulously stitching molecules together. None of this would astonish the atoms themselves if they could marvel. They did not know they are part of a human, a tree, or a distant nebula. Yet their indifference is what makes them miraculous universal soldiers, obeying simple rules, creating complexity, not by intention, but by inevitable consequence. As you read these words, atoms within your eyes absorb light, triggering electrical signals that carve meaning from the void. The screen before you hums with their activity, its pixels glowing through the precise excitation of phosphors or LEDs. And so, begin here, not at the edge of the universe, but at the foundation of everything within it. Atoms are the lexicon of reality, the unspoken language whispered by rocks, stars, and living flesh. To study them is to decipher the first principles of existence, to glimpse the architecture hidden beneath the skin of the visible world, as we venture further into the heart of chemistry. Remember this: you are a temporary congregation of these ancient particles, fleeting arrangement and an endless rearrangement. And yet, within you, they conspire to create something extraordinary, consciousness itself, wandering back at the atoms that compose it. Thus begins our journey, not with a bang, but with a quiet acknowledgement of the small, the simple, and the profoundly significant. The building blocks are here. Let us see what they've built. In the silent heart of every atom lies a story of forces and paradoxes, where the familiar laws of physics twist into something strange and marvelous. Picture, if you will, a miniature universe. Its center occupied by a nucleus so dense that a teaspoon of it would weigh as much as a mountain. This nucleus, though unimaginably small, is the anchor around which the atom's identity is built. Here, protons and neutrons huddle together, bound by forces strong enough to overcome the repulsion between positively charged protons. Protons, the carriers of positive charge, define the atom's elemental identity: 1 proton for hydrogen, 6 for carbon, 8 for oxygen. Change the number, and the atom transforms into something entirely different, a new element with its own unique story. Neutrons, their neutral companions, act as peacekeepers, adding mass and stability without altering the atom's charge. Without them, the nucleus would fly apart under the sheer repulsion of protons, and the delicate balance of matter would collapse. Yet, the nucleus is only part of the tale. Surrounding it, at distances vast compared to its size, electrons whirl in a frenetic dance. These tiny particles, negatively charged, are the true artists of chemistry. They exist in a state of perpetual motion, occupying regions of space known as orbital clouds of probability, where they are most likely to be found. Unlike planets orbiting the sun, electrons do not follow neat, predictable paths. Instead, they move in waves, their positions and momenta governed by the strange rules of quantum mechanics. The farther an electron is from the nucleus, the more energy it holds, and the more easily it can break free to form bonds with other atoms. It is these electrons, with their ability to leap, share, and transfer between atoms, that make chemistry possible. They are the architects of molecules, the mediators of reactions, and the silent partners in every chemical transformation. What makes this arrangement even more astonishing is how empty the atom truly is. If the nucleus were the size of a marble, the electrons would orbit at a distance comparable to a football field. The solidity we perceive in objects, the firmness of a table, the resistance of a wall, an illusion, born not from compact matter but from the interactions of these ghostly particles. When you place your hand on a surface, it is not material touching material, but the electromagnetic forces between electrons pushing back against each other, creating the sensation of solidity. In this way, atoms are both overwhelmingly empty and yet brimming with potential. Their structure, a masterpiece of nature's ingenuity. Protons, neutrons, and electrons each play their roles with unerring precision. Protons define the element and its chemical behavior. Neutrons stabilize the nucleus, and electrons dictate how atoms interact with one another. The number of protons determines the atom's place on the periodic table, while the number of neutrons can vary, giving rise to isotopes atoms of the same element with different masses. Some isotopes are stable, enduring unchanged through the ages. Others are unstable, their nuclei decaying over time, releasing energy in the process. These radioactive atoms, though often feared, are essential in applications from medicine to archaeology. Their decays acting as clocks that tell the story of Earth's past. The dance of Coquette, the dance of electrons, is perhaps the most enchanting part of this atomic ballet. Electrons occupy distinct energy levels or shells, each capable of holding a specific number of electrons. The first shell holds up to 2 electrons, the second up to 8, and so on. Atoms strive to fill their outermost shells, seeking stability through bonding. Some atoms donate electrons, others accept them, and still others share them, creating the rich tapestry of compounds that fill our world. The behavior of these electrons is not just academic hit, it's the reason salt tastes salty. It's why metals conduct electricity, and why diamonds are hard while graphite is soft. The same carbon atoms, arranged differently, yield materials with wildly different properties, all because of how their electrons are shared or transferred. Amidst this complexity, one truth emerges: the atom is not a static, unchanging entity, but a dynamic system, humming with energy and interaction. Its structure, so minute as to be invisible to the naked eye, governs the vastness of the cosmos and the intricacy of life. Every breath you take, every thought you form, is made possible by the precise arrangement of these particles, protons, neutrons, and electrons working in harmony. And so, as we delve deeper into the heart of chemistry, remember this: the structure of the atom is not just a scientific concept. It is the foundation upon which reality itself is built. A silent symphony played out in every grain of sand, every drop of water, every living cell. The closer we look, the more we realize that the universe is not a collection of separate objects, but a web of interconnected particles, each one playing its part in the grand unfolding story of existence. At the center of every atom, hidden deep within its whirling cloud of electrons, lies a secret so profound it defies ordinary comprehension. The nucleus, a speck so tiny it would take 1,000,000 atoms lined up to span its width, holds nearly all the atom's mass and all its elemental identity. If atoms were cities, the nucleus would be a single grain of sand at its core, yet this grain contains a density so staggering that, if it could be held in human hands, it would crush through the floor and sink toward the center of the earth. This is the heart of the atom, the anchor of matter, where protons and neutrons bind together in a force older than the stars themselves. Protons, positively charged and furious in their repulsion against one another, should by all known laws of electromagnetism explode outward in an instant. That they do not is one of nature's greatest acts of defiance. The nucleus stays intact because of a force stronger than electricity, stronger than magnetism, a force so potent it was named simply the strong nuclear force. It is this invisible glue that overcomes the violent push between protons, binding them to their neutral partners, the neutrons, in a pact so tight that not even the immense heat of the sun's core can easily break it. Without this force, matter as we know it would not exist. No stars could burn, no planets could form, no molecules could weave together to create life. The nucleus is more than just a dense cluster of particles. It is a record keeper. The number of protons within it dictates the atom's identity. A single proton makes hydrogen, the element that fuels stars and fills the vast emptiness of space. 6 protons forge carbon, the backbone of every living thing. 26 protons create iron, whose silent formation in dying stars signals their impending supernova death. Change the proton count by even 1, and the atom becomes something entirely new, a different element with different properties, a different role in the universe's grand story. Neutrons, though electrically neutral, are far from passive. They are the peacekeepers of the nucleus, adding stability without altering the atom's charge. In small atoms, protons and neutrons exist in roughly equal numbers, but as atoms grow larger, more neutrons are needed to hold the nucleus together. Too few neutrons, and the nucleus becomes unstable, prone to radioactive decay. Too many, and the same instability arises. The delicate balance between protons and neutrons is what allows heavier elements like gold, uranium, and lead to exist at all. Some of these nuclei last for billions of years, others decay in fractions of a second. Their fleeting existence a testament to the fine-tuning of the cosmos. But the nucleus is not static. It thrums with energy, vibrating under the strain of its own crowded particles. In radioactive atoms, this strain becomes too much. The nucleus lurches, spitting out particles or energy in an attempt to find stability. These decays, though invisible to the naked eye, have shaped our world. The heat of Earth's core, the dating of ancient rocks, the energy released in nuclear reactors all owe their existence to nuclei adjusting, rearranging, and shedding pieces of themselves over time. Even our own bodies contain traces of radioactive atoms, remnants of the stars that once forged them. Their slow decays, a whisper of the universe's violent birth. To truly grasp the density of the nucleus, imagine compressing the entire mass of a skyscraper into a single raindrop. The nucleus is that concentrated, its particles packed so tightly that they cease to behave like individual entities, and instead merge into a churning sea of quark-like matter. Neutron stars, the collapsed cores of dead suns, offer a glimpse of this density on a cosmic scale. A single sugar cube's worth of neutron star material would weigh as much as a mountain. The nucleus, though far smaller, operates under the same bewildering principles. Yet, for all its robustness, the nucleus is also strangely delicate. Disturb it with enough energy, and it can split a process known as nuclear fission, which releases energy powerful enough to light cities or devastate them. Alternatively, nuclei can fuse together, as they do in the hearts of stars, merging to create heavier elements and bathing the cosmos in light. These reactions, fission and fusion, are the universe's two great nuclear engines. The first, unraveling heavy nuclei, the second, building them up. Without them, the periodic table would stop at hydrogen, and the rich diversity of elements that make up planets, oceans, and life would never have existed. What is most humbling is that nuclei do not know they are part of anything larger. A gold nucleus in a wedding ring does not know it is in jewelry. An oxygen nucleus in your lungs does not know it sustains your life. They simply exist, following laws written into the fabric of reality since the first seconds of the universe. Yet their obedience to these laws creates everything we see and touch: the solidity of metals, the transparency of glass, the softness of fabric. The nucleus, though hidden, is the unspoken ruler of chemistry. Its protons dictate how atoms bond. Stability determines which elements persist and which fade away. The carbon in your cells, the iron in your blood, titanium in your bones, all were sculpted in the hearts of long-dead stars, their nuclei, forged in cosmic furnaces and scattered across the galaxy. You are, in a very real sense, made of stardust, assembled into consciousness by atoms that have existed longer than Earth itself. As we peel back more layers of the atom story, this truth becomes ever clearer. The nucleus is not just the heart of the atom, it is the heart of everything. From the tiniest grain of sand to the vast sprawl of galaxies, all of it circles back to these minuscule, indomitable knots of matter, pulsing silently at the center of all things. In the intricate dance of atomic structure, electrons emerge as the most dynamic and unpredictable participants, while protons and neutrons form the stable core of the nucleus. Electrons flit about in a realm of uncertainty, embodying the very essence of chemistry's complexity. These tiny, negatively charged particles are not merely accessories to the atom. They are the social butterflies of the atomic world, caging in a constant ballet of movement and interaction that defines the behavior of matter itself. Their significance extends far beyond their size, as they govern the ways in which atoms bond, react, decay, and ultimately shape the universe around us. Electrons exist in a cloud-like formation around the nucleus, occupying regions known as orbitals. Unlike the planets that orbit a sun in predictable paths, electrons do not follow fixed trajectories. Instead, they inhabit a probabilistic landscape where their exact position at any given moment is uncertain. This is a fundamental principle of quantum mechanics, which describes the behavior of particles at the atomic and subatomic levels. The concept of orbitals reflects this uncertainty, as they represent areas where electrons are likely to be found, rather than precise locations. Each orbital has a specific shape and energy level, and the arrangement of electrons within these orbitals determines an atom's chemical properties. The energy levels of electrons are crucial to understanding how atoms interact with one another. Electrons occupy different shells, with each shell corresponding to a specific energy level. The first shell, closest to the nucleus, can hold a maximum of 2 electrons, while the second shell can accommodate up to 8. As you move further from the nucleus, the shells can hold more electrons, but they also require more energy to occupy. This hierarchical structure creates a framework for how atoms bond and react, as atoms strive to achieve stability by filling their outermost shells. Atoms are most stable when their outer shell is full, a condition often referred to as the octet rule. This drive for stability is what fuels the interactions between atoms, leading to the formation of chemical bonds. When an atom has a nearly full outer shell, it may seek to gain or share electrons with other atoms to achieve that coveted state of balance. Conversely, if an atom has only a few electrons in its outer shell, it may be eager to lose them, forming bonds that allow it to reach a more stable configuration. This quest for stability is the foundation of chemical reactions, where electrons are transferred or shared, creating new substances and altering the very fabric of matter. The behavior of electrons during these interactions is nothing short of fascinating. When atoms come together to form a bond, they engage in a delicate negotiation, sharing or transferring electrons in a way that satisfies both parties. In covalent bonds, atoms share electrons equally, creating a strong connection that holds them together. This type of bonding is common among nonmetals, where the sharing of electrons allows for the formation of complex molecules, such as water or glucose. In contrast, ionic bonds occur when one atom donates an electron to another, resulting in the formation of charged ions. The electrostatic attraction between these oppositely charged ions creates a strong bond, simplified by the formation of table salt from sodium and chlorine. Electrons are also responsible, for the unique properties of materials. The way electrons are arranged and how they interact with one another dictate whether a substance is a solid, liquid, or gas. For instance, metals possess a sea of electrons that allows them to conduct electricity and heat efficiently. In metals, electrons are not bound to any specific atom. Instead, they move freely throughout the structure, creating a communal pool that facilitates conductivity. This is why metals are often shiny and malleable, able to be shaped without breaking. The behavior of electrons in metals contrasts sharply with that of nonmetals, which tend to form more rigid structures due to their tendency to share or transfer electrons rather than allowing them to roam freely. The role of electrons extends beyond mere bonding. They are also the driving force behind chemical reactions. When a reaction occurs, it is often the electrons that are either excited or displaced, leading to the formation of new products. For example, when a flame heats a substance, the added energy can excite electrons, causing them to jump to higher energy levels. When these excited electrons return to their original state, they release energy in the form of light. This phenomenon is the basis for fireworks, where the colors produced are a result of different metal ions emitting light as their electrons transition between energy levels. Moreover, the behavior of electrons is influenced by external factors, such as temperature and pressure. Increasing the temperature provides electrons with more energy, allowing them to move more freely and collide with other atoms more frequently. This increased activity can accelerate chemical reactions, leading to faster rates of change. Conversely, lowering the temperature can slow down electron movement, reducing the likelihood of collisions and, consequently, the rate of reactions. Pressure also plays a role, particularly in gaseous reactions, where increasing pressure forces particles closer together, enhancing the chances of interaction. As we delve deeper into the world of electrons, we begin to appreciate their role in the broader context of chemistry and life itself. The intricate dance of electrons is not just a series of random movements. It is a carefully orchestrated performance that shapes the very essence of existence, from the formation of complex organic molecules to the simple act of breathing. Electrons are at the heart of every process, every reaction, and every interaction in the grand tapestry of the universe. Electrons are the threads that weave together the fabric of reality. They are the catalysts of change, the architects of bonds, and the silent participants in the ongoing drama of chemistry. As we continue our exploration of the atomic world, let us remember the significance of these social butterflies. Its behavior and interactions define not only the elements, but also the very essence of life itself. The concept of atomic space presents one of the most paradoxical truths about the nature of matter. When we observe the solid objects around us, the chair we sit on, the book we read, even our own hands, they appear perfectly whole and continuous to our senses. Yet, at the most fundamental level, these objects are composed almost entirely of empty space, a revelation that fundamentally alters our understanding of physical reality. This apparent solidity we experience is nothing more than an elaborate illusion created by electromagnetic interactions between the tiny charged particles that make up atoms. To comprehend the true nature of atomic space, we must first examine the structure of the atom in detail. Each atom consists of a positively charged nucleus surrounded by a cloud of negatively charged electrons. The nucleus, containing protons and neutrons, accounts for nearly all of an atom's mass while occupying only a minuscule fraction of its volume. If we were to magnify an atom to the size of a football stadium, the nucleus would be no larger than a grain of sand at the center, while the electrons would be like dust particles swirling through the empty stands. This incredible ratio of mass to volume means that matter is composed of about 99.9% empty space, with all the actual stuff concentrated in vanishingly small particles. The implications of this atomic emptiness are profound and far-reaching. Our everyday experience of solidity arises not from physical contact between atoms, but rather from electromagnetic forces. When two objects come into contact, their electron clouds repel each other with a force strong enough to prevent interpenetration. These electromagnetic interactions create the sensation of hardness and impenetrability that we interpret as solid matter. At the quantum level, objects don't actually touch in the way we intuitively imagine. They merely approach closely enough for their electromagnetic fields to interact significantly. This understanding of atomic space revolutionizes our conception of matter's fundamental nature. The chair you're sitting on doesn't actually support you through physical contact in the traditional sense. Instead, the electrons in the atoms of your body repel the electrons in the atoms of the chair with sufficient force to counteract gravity's pull. Similarly, when you run your hand across a table surface, what you perceive as smooth continuity is actually the interaction of electromagnetic fields between the electron clouds of your skin, blue, and those of the table's surface atoms. The empty nature of atomic space also explains many of matter's unusual properties. For instance, it accounts for why we can compress gases much more easily than liquids or solids. In gaseous state, atoms are already far apart with vast empty spaces between them, allowing the atomic structures to be pushed closer together. In solids and liquids, atoms are already packed much closer, with their electron clouds in near contact, making further compression exceedingly difficult without applying extraordinary pressure. Gold's remarkable malleability, allowing it to be hammered into thin leaves only a few hundred atoms thick, also stems from this underlying atomic spaciousness that permits rearrangement of atomic positions without structural failure. Nanotechnology exploits this empty space between atoms to remarkable effect. Scientists can now manipulate individual atoms, positioning them with precision to create novel materials and structures. The ability to move atoms relies on their essentially empty nature. There is space to maneuver individual particles within and between atoms. This technology could not exist if atoms were solid in the way we traditionally imagined them to be. The concept of atomic space also sheds light on fundamental forces in nature. While gravity dominates at macroscopic scales, it becomes negligible at atomic scales, where electromagnetic forces between charged particles prevail. The fact that atoms are mostly empty space explains why gravity, though affecting all mass, doesn't collapse matter into infinitesimal points. Electromagnetic repulsion between electrons at the atomic level creates stability against gravitational collapse, allowing matter to maintain its structure and volume. Perhaps most remarkably, the emptiness within atoms means that all matter, our bodies, the Earth, even massive stars, could theoretically be compressed to incredibly small volumes if the empty space were removed. A neutron star provides a dramatic astronomical example of this principle, where atomic nuclei are crushed together so tightly that the star's matter reaches densities where a single teaspoonful would weigh billions of tons on Earth. This extreme state of matter demonstrates just how much empty space ordinarily exists between and within atoms under normal conditions. The nature of atomic space has significant implications for quantum mechanics and our understanding of reality. Particles at the quantum level don't behave like classical objects. They can tunnel through barriers, exist in superposition, and become entangled in ways that defy classical intuition. Much of this bizarre behavior arises because particles aren't localized points, but rather exist as probability distributions spread through space. An electron doesn't orbit a nucleus like a planet around the sun, but exists as a wave function describing the probability of finding it at any given point in the electron cloud. This quantum mechanical view of atomic structure leads to even more counterintuitive implications. In some interpretations of quantum physics, the empty space within atoms isn't truly empty at all, but teeming with virtual particles popping in and out of existence, quantum fluctuations, and potential energy. What appears empty at one scale reveals incredible complexity and activity at another. The vacuum of space itself, far from being nothingness, is now understood by physicists to contain enormous amounts of fluctuating energy. On a practical level, the teeming nature of atomic space enables the phenomenon of radioactive decay, where unstable atoms eject particles to achieve greater stability. Alpha decay, in particular, demonstrates this beautifully. As alpha particles, helium nuclei must escape the atom's confines, despite apparently not having enough energy to overcome nuclear forces. Quantum tunneling allows this to occur because the alpha particle isn't strictly confined within the nucleus. Its wave function extends into the surrounding space, giving it some probability of appearing beyond the nuclear force's range. The empty space within atoms also plays a crucial role in chemical bonding and molecular formation. When atoms bond to form molecules, their electron clouds interact and rearrange to create new probability distributions. Covalent bonds represent shared electron probability between atoms, while ionic bonds involve complete transfer of electrons from one atom to another with subsequent electrostatic attraction. In all cases, it's the nature of electron probability distributions extending into the empty space around nuclei that enables these critical interactions. Modern imaging technologies like scanning, tunneling, microscopes allow us to visualize this atomic structure directly. These instruments work by detecting the electron probability clouds at a material surface, effectively mapping where electrons are likely to be found, rather than imaging the atoms themselves. The images they produce show fuzzy clouds of probability, rather than hard, well-defined spheres, confirming the fundamentally spread out and empty nature of atomic structure. The implications extend even to our understanding of light and electromagnetic radiation. The reason light can pass through some materials like glass while being blocked by others like metals depends on how the electrons are arranged in each material's atoms and how those electrons interact with photons, key in transparent materials. The electrons are bound in such a way that visible light photons pass through the enormous empty spaces between atomic nuclei without interacting significantly with the electrons. In opaque materials, electrons are arranged to absorb and reflect photons, preventing their passage through what is still fundamentally empty space at the atomic level. Understanding atomic space also helps explain why matter has distinct phases: solid, liquid, gas, plasma, despite being composed mostly of nothingness. In solids, the pattern of atomic arrangement is fixed because the electromagnetic interactions create rigidity, though the atoms themselves remain mostly empty space with electrons whizzing about. In liquids, these interactions allow more movement, while maintaining proximity between atoms. In gases, atoms move freely through mostly empty space, interacting only occasionally. The behavior of each phase depends not on the solidness of the atoms themselves, but on the strength and nature of the electromagnetic interactions between their electron clouds. Perhaps most philosophically challenging is what this means for our perception of reality. Every solid object we see, touch, and interact with is fundamentally no more substantial than a ghostly collection of energy fields and probability distributions. The apparent solidity of matter emerges from patterns of interaction between these immaterial components, not from any inherent material substance. This realization forces us to reconsider basic assumptions about the nature of physical existence and what it means for something to be real or solid. The emptiness within atoms isn't passive void, but a complex arena of dynamic interactions. Quantum field theory describes it as brimming with potentiality, where particles emerge and vanish, where forces manifest through exchange particles, K, and where the fundamental structure of reality plays out. This active emptiness at the heart of matter gives rise to all the complexity and diversity we observe in the material world, from the simplest hydrogen atom to the most complex organic molecules. Everything we know emerges from patterns of interaction within and between mostly empty atomic structures. Looking to the future, understanding of atomic space may enable revolutionary technologies. Materials with designed atomic structures could lead to superconductors that work at room temperature, ultra-strong and lightweight construction materials, or medical treatments that manipulate matter at the most fundamental level. Quantum computing directly exploits the probabilistic nature of particles in this space to perform calculations impossible for classical computers. As our control over atomic scale structures improves, we may find ways to harness the empty space within atoms for energy production, transportation, or communication technologies beyond our current imagination. The nature of atomic space ultimately connects to some of the deepest questions in physics today. Dark matter and dark energy, together constituting about 95% of the universe's total content, may interact with the empty space within atoms in ways we don't yet understand. Theories of quantum gravity attempt to reconcile the apparent emptiness of atoms with space-time's curvature described by general relativity. The mystery of why empty space has vacuum energy, and how this relates to the cosmological constant remains one of physics' greatest challenges in this light. The simple realization that atoms are mostly empty space becomes a gateway to understanding the fundamental nature of reality. From this perspective, the solid, stable world we perceive is a kind of collective illusion emerging from patterns of interactions in the void. The empty space within atoms is not mere absence, but the stage upon which the universe's entire material drama unfolds. It's an insight that continues to inspire awe and drive scientific inquiry into matter's deepest mysteries. The periodic table is one of the most significant achievements in the history of science. Serving as a comprehensive character map of the elements that make up our universe, it organizes the known elements based on their atomic number, electron configuration, and recurring chemical properties. This systematic arrangement not only provides a framework for understanding the behavior of individual elements, but also reveals the relationships between them, allowing scientists to predict how they will interact in chemical reactions. At its core, the periodic table is divided into rows called periods and columns, known as groups or families. Elements in the same group share similar chemical properties due to their similar electron configurations, particularly in their outermost shells. For example, the alkali metals in group 1 are highly reactive and tend to lose one electron during chemical reactions, while the noble gases in group 18 are inert and do not readily form compounds due to their full outer electron shells. This organization highlights the periodicity of elemental properties, a concept that underpins much of modern chemistry. The periodic table is not static. It has evolved over time as new elements have been discovered and our understanding of atomic structure has deepened. The early versions of the table were based on atomic mass, but the modern periodic table is organized by atomic number, which reflects the number of protons in an atom's nucleus. This shift was crucial in resolving discrepancies in the properties of elements and ensuring that the table accurately represented the relationships between them. Each element in the periodic table is represented by a unique symbol, typically derived from its name in English or Latin. For instance, hydrogen is denoted by H, while sodium is represented by Na from its Latin name, natrium. The table also includes important information about each element, such as its atomic number, atomic mass, and state of matter at room temperature. This wealth of information makes the periodic table an invaluable resource for chemists and students alike. The periodic table also serves as a guide for understanding chemical reactions and the formation of compounds. By examining the position of elements within the table, one can predict how they will behave in reactions. For example, elements on the left side of the table, such as metals, tend to lose electrons and form positive ions, while elements on the right side, such as nonmetals, tend to gain electrons and form negative ions. This knowledge is essential for predicting the products of chemical reactions and understanding the principles of bonding. Moreover, the periodic table is a testament to the interconnectedness of the elements. The relationships between elements are not merely academic. They have real-world implications. For instance, the transition metals, located in the center of the table, are known for their ability to form complex ions and act as catalysts in various chemical reactions. Their unique properties make them essential in industrial processes, from the production of fertilizers to the manufacturing of electronics. As we explored the periodic table further, we encountered the concept of periodic trends patterns that emerge as we move across periods or down groups. These trends include atomic radius, ionization energy, and electronegativity, each of which provides insight into the behavior of elements. For example, as we move from left to right across a period, the atomic radius decreases due to the increasing positive charge of the nucleus, which pulls the electrons closer. Conversely, as we move down a group, the atomic radius increases due to the addition of electron shells. The periodic table is not just a collection of elements. It is a dynamic representation of the underlying principles of chemistry. It encapsulates the relationships between elements, their properties, and their behaviors in a way that is both systematic and intuitive. As we continue our journey through the world of chemistry, the periodic table will serve as our guide, illuminating the connections between the elements and the intricate dance of atoms that shapes our universe. One of the most fascinating aspects of the periodic table is its ability to predict the existence and properties of elements that had not yet been discovered at the time of its formulation. Dmitri Mendeleev, who was credited with creating the first widely recognized periodic table in 1869, left gaps in his table for elements that he predicted would be discovered later. His predictions were remarkably accurate, as evidenced by the eventual discovery of gallium and germanium, which fit perfectly into the spaces he had reserved for them. This predictive power of the periodic table underscores significance as a tool for scientific inquiry and exploration. The periodic table also highlights the concept of periodicity, which refers to the recurring trends in elemental properties as one moves across the table. For instance, the reactivity of alkali metals increases as you move down the group, with cesium being more reactive than lithium. Similarly, the electronegativity of nonmetals tends to increase as you move from left to right across a period, with fluorine being the most electronegative element. These trends are not arbitrary, okay? They arise from the underlying atomic structure and the behavior of electrons in different elements, in addition to chemical properties. The periodic table also provides insights into the physical properties of Ku elements. For example, metals, which are typically found on the left side of the table, are characterized by their malleability, ductility, and conductivity. In contrast, nonmetals, located on the right side, are generally brittle and poor conductors of heat and electricity. Metalloids, which lie along the zigzag line that separates metals and nonmetals, exhibit properties of both categories, making them valuable in various applications, such as semiconductors and electronics. The periodic table is also a reflection of the historical development of chemistry as a science. The discovery of new elements and the understanding of their properties have been pivotal in shaping our knowledge of the natural world. For instance, the identification of noble gases in the late 19th century expanded the periodic table and challenged existing theories about chemical reactivity. The noble gases, with their complete outer electron shells, were found to be largely inert, leading to a deeper understanding of the role of electron configuration in chemical behavior. As we delve deeper into the periodic table, we encounter the concept of isotopes, atoms of the same element that have different numbers of neutrons. Isotopes can have significant implications for both chemistry and physics. For example, carbon-14, a radioactive isotope of carbon, is used in radiocarbon dating to determine the age of ancient organic materials. Understanding isotopes allows scientists to explore a wide range of applications. From medicine to archaeology, the periodic table also plays a crucial role in the field of biochemistry, where the elements it contains are the building blocks of life. Elements such as carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur are essential for the formation of biomolecules like proteins, nucleic acids, and carbohydrates. The unique properties of these elements, as revealed by their positions in the periodic table, dictate how they interact and combine to form the complex structures necessary for life. In recent years, advancements in technology have allowed scientists to synthesize new elements that do not occur naturally on Earth. These synthetic elements, often referred to as super-heavy elements, are created in laboratories through nuclear reactions. The study of these elements provides valuable insights into the limits of the periodic table and the fundamental forces that govern atomic behavior. As researchers continue to explore the properties of these newly created elements, they may uncover new phenomena that challenge our understanding of chemistry and physics. The periodic table is not just a static reference. It is a living document that continues to evolve as our understanding of the elements deepens. Ongoing research in fields such as materials, science, nanotechnology, and quantum chemistry is constantly reshaping our knowledge of elemental properties and their applications. As we uncover new elements and explore their unique characteristics, the periodic table will undoubtedly expand, reflecting the ever-growing complexity of the natural world. In conclusion, the periodic table serves as a character map of the elements, providing a systematic framework for understanding their properties and behaviors. Its organization reveals the relationships between elements, allowing scientists to predict how they will interact in chemical reactions. The periodic table is a testament to the interconnectedness of the elements and the underlying principles of chemistry that govern their behavior. As we continue our exploration of the atomic world, the periodic table will remain an invaluable tool, guiding us through the intricate dance of atoms that shapes our universe. The journey through the periodic table is not just an academic exercise. It is a profound exploration of the fundamental nature of matter and the intricate web of relationships that define the physical world around us. Quantum mechanics represents a revolutionary shift in our understanding of the atomic world, fundamentally altering how we perceive the behavior of matter at its most basic level. Unlike classical physics, which describes particles as having definite positions and velocities, quantum mechanics introduces a probabilistic framework. This means that at the atomic scale, particles, such as electrons, do not have fixed locations or paths. Instead, they exist in a state of probability, described by wave functions. These wave functions provide a mathematical representation of the likelihood of finding an electron in a particular region around the nucleus of an atom. One of the most intriguing aspects of quantum mechanics is the concept of wave-particle duality. Electrons, which were once thought to behave solely as particles, also exhibit wave-like properties. This duality is best illustrated by the famous double-slit experiment, where electrons create an interference pattern when not observed, suggesting they behave as waves. However, when measured, they appear as discrete particles. This phenomenon challenges our classical intuitions and highlights the strange nature of quantum reality. The Heisenberg uncertainty principle further complicates our understanding of atomic behavior. It states that there is a fundamental limit to how precisely we can know both the position and momentum of a particle simultaneously. This principle implies that the act of measurement itself influences the system being observed. In the context of atoms, this means that while we can predict the probability of finding an electron in a certain region, we cannot pinpoint its exact location and momentum at the same time. Quantum mechanics also introduces the concept of quantization, where certain properties, such as energy, can only take on discrete values. In atoms, electrons occupy specific energy levels, and transitions between these levels result in the absorption or emission of photons. This quantized nature of energy levels explains the distinct spectral lines observed in atomic emission and absorption spectra. Each element has a unique set of energy levels, leading to its characteristic spectral fingerprint. The implications of quantum mechanics extend beyond theoretical physics. They have profound effects on chemistry and material science. The behavior of electrons in atoms determines how they bond with one another, leading to the formation of molecules. The shapes of these molecules, dictated by the arrangement of atomic orbitals, influence their chemical properties and reactivity. Understanding quantum mechanics allows chemists to predict and manipulate chemical reactions, paving the way for advancements in fields such as pharmaceuticals, materials science, and nanotechnology. Moreover, quantum mechanics has led to the development of groundbreaking technologies. Quantum computing, for instance, leverages the principles of superposition and entanglement to perform calculations at speeds unattainable by classical computers. Quantum dots, tiny semiconductor particles, are used in displays in solar cells, showcasing the practical applications of quantum principles in everyday technology. As we delve deeper into the realm of quantum mechanics, we encounter philosophical questions about the nature of reality itself. The observer effect raises intriguing discussions about the role of consciousness in measurement and the implications of multiple realities, as suggested by interpretations like the many-worlds hypothesis. These discussions challenge our understanding of existence and the fundamental nature of the universe. In conclusion, quantum mechanics is not just a set of abstract principles. It is a framework that reshapes our understanding of atomic behavior and the interactions that govern the material world. As we continue to explore this fascinating field, we uncover new layers of complexity and beauty, revealing the intricate dance of particles that constitutes the fabric of our universe. The journey through quantum mechanics is one of wonder and discovery, inviting us to question our perceptions and embrace the mysteries that lie at the heart of reality. In the intricate world of chemistry, electrons play a pivotal role, acting as the primary agents of chemical bonding and reactivity. To understand the behavior of these elusive particles, one must delve into the concept of electron clouds and orbitals, which provide a framework for visualizing where electrons are likely to be found around an atomic nucleus. Unlike the classical notion of electrons orbiting the nucleus in fixed paths, quantum mechanics reveals a more complex and unpredictable nature, characterized by the probabilistic distribution of electron density. At the heart of this discussion lies the concept of electron clouds. Rather than existing in defined orbits, electrons inhabit regions of space where their presence is most probable. These regions are represented by electron clouds, which can be visualized as fuzzy, three-dimensional shapes surrounding the nucleus. The density of the cloud at any given point indicates the likelihood of finding an electron there. This visualization challenges our classical intuitions, as it emphasizes that electrons do not have precise locations, but rather exist in a state of probability. The shapes of these electron clouds are determined by atomic orbitals, which are mathematical functions derived from the wave functions of electrons. Each orbital corresponds to a specific energy level and shape. It's characterized by quantum numbers that describe its size, shape, and orientation in space. The four types of orbitals S, P, D, and Phi have distinct shapes and energy levels. The S orbitals are spherical, while P orbitals have a dumbbell shape. D orbitals are more complex, and F orbitals exhibit even more intricate geometries. These shapes are not merely abstract concepts. They have profound implications for how atoms interact and bond with one another. The arrangement of electrons in these orbitals follows the principles of quantum mechanics, particularly the Pauli exclusion principle and Hund's rule. The Pauli exclusion principle states that no two electrons in an atom can have the same set of quantum numbers. This means that each orbital can hold a maximum of 2 electrons with opposite spins. Hund's rule, on the other hand, dictates that electrons will fill degenerate orbitals, those with the same energy, one at a time, before pairing up. This arrangement minimizes electron-electron repulsion and stabilizes the atom. As we explored the dance of electrons within these orbitals, we encountered the concept of hybridization, which describes the mixing of atomic orbitals to form new hybrid orbitals. This process is crucial in understanding molecular geometry and bonding. For instance, in carbon, the mixing of one s orbital and 3 p orbitals results in 4 equivalent sp³ hybrid orbitals, which arrange themselves in a tetrahedral geometry. This hybridization explains the formation of diverse organic compounds. In the complexity of biological molecules, the unpredictable nature of electrons is further highlighted by their ability to participate in chemical reactions. When atoms come together to form molecules, the interactions between their electron clouds dictate the strength and type of bonds formed. Covalent bonds arise from the sharing of electron pairs between atoms, while ionic bonds result from the transfer of electrons from one atom to another. The behavior of electrons during these processes is influenced by their energy levels, the electronegativity of the atoms involved, and the overall stability of the resulting configuration. Moreover, the concept of resonance plays a significant role in understanding the behavior of electrons in certain molecules. Resonance occurs when a molecule can be represented by 2 or more valid Lewis structures, each depicting different arrangements of electrons. The true structure of the molecule is a hybrid of these resonance forms, reflecting the delocalization of electrons across multiple bonds. This delocalization contributes to the stability and reactivity of molecules, as seen in aromatic compounds where electrons are shared across a cyclic structure. As we delve deeper into the dance of electrons, we must also consider the role of external factors such as electromagnetic fields and temperature, which can influence electron behavior. For instance, when exposed to light, electrons can absorb energy and transition to higher energy levels, a phenomenon known as excitation. This process is fundamental to various applications, including photosynthesis, where chlorophyll molecules capture light energy to drive chemical reactions. The unpredictable nature of electrons also extends to their interactions with other particles. Quantum entanglement, a phenomenon where the states of 2 or more particles become correlated, illustrates the interconnectedness of electrons across distances. When 2 electrons are entangled, measuring the state of one instantaneously affects the state of the other, regardless of the distance separating them. This phenomenon challenges our classical understanding of locality, and has profound implications for quantum computing and information transfer. In summary, it's a dance of electrons. It's a complex interplay of probability, energy, and interaction. The concept of electron clouds and orbitals provides a framework for understanding the behavior of these fundamental particles, revealing their unpredictable nature and the intricate patterns they form. As we continue to explore the world of electrons, we uncover the underlying principles that govern chemical bonding, molecular structure, and the very fabric of matter itself. The journey through this quantum landscape invites us to appreciate the beauty and complexity of the atomic world, where the dance of electrons shapes the universe around us. Chemical bonds are the forces that hold atoms together, forming the molecules and compounds that constitute the vast array of substances in our universe. Understanding these bonds is essential for grasping the principles of chemistry, as they dictate the properties, behaviors, and interactions of matter. In this chapter, we will explore the three primary types of chemical bonds: covalent, ionic, and metallic, each characterized by distinct mechanisms of interaction and unique implications for the properties of the resulting compounds. Covalent bonds arise from the sharing of pairs between atoms. This type of bond typically occurs between nonmetals, which have similar electronegativities and a tendency to gain electrons. When two nonmetals approach each other, their electron clouds overlap, allowing them to share electrons and achieve a more stable electronic configuration. The shared electrons occupy molecular orbitals that belong to both atoms, creating a bond that holds them together. The strength of a covalent bond is influenced by the number of shared electron pairs. Single bonds involve one pair of electrons. Double bonds involve two pairs, and triple bonds involve three pairs. As the number of shared pairs increases, the bond becomes stronger and shorter, resulting in a more stable molecule. One of the most well-known examples of covalent bonding is found in water, HO. In this molecule, each hydrogen atom shares one electron with the oxygen atom, resulting in two covalent bonds. The bent shape of the water molecule, due to the repulsion between the lone pairs of electrons on the oxygen atom, gives rise to its unique properties, such as its high boiling point and ability to dissolve many substances. Covalent bonds can also lead to the formation of complex structures, such as proteins and DNA, where the specific arrangement of atoms and bonds determines the function and behavior of these biological molecules. In contrast to covalent bonds, ionic bonds are formed through the transfer of electrons from one atom to another. This type of bond typically occurs between metals and nonmetals, where the metal atom donates one or more electrons to achieve a stable electron configuration, while the nonmetal atom accepts those electrons. The resulting charged particles, known as ions, are held together by electrostatic forces of attraction. The metal becomes a positively charged cation, while the nonmetal becomes a negatively charged anion. This transfer of electrons creates a strong ionic bond, resulting in the formation of ionic compounds. A classic example of ionic bonding is found in sodium chloride, NaCl, commonly known as table salt. In this compound, sodium Na donates one electron to chlorine Cl, resulting in the formation of Na and Cl ions. The electrostatic attraction between these oppositely charged ions creates a strong ionic bond, resulting in a crystalline lattice structure. Ionic compounds typically exhibit high melting and boiling points due to the strength of the ionic bonds, and they often dissolve in water, dissociating into their constituent ions. This property is crucial for many biological processes, as ions play essential roles in cellular function and signaling. Metallic bonds, on the other hand, are characterized by a unique arrangement of atoms in a lattice structure, where electrons are not associated with any specific atom but are instead delocalized throughout the metal. This sea of electrons allows for the free movement of electrons, which contributes to the distinctive properties of metals, such as electrical conductivity, malleability, and ductility. K. In metallic bonding, metal atoms release some of their valence electrons, creating positively charged metal cations surrounded by a cloud of delocalized electrons. This arrangement allows metals to conduct electricity efficiently. Quote, as the free-moving electrons can carry an electric current, the properties of metallic bonds can be observed in everyday materials. For instance, copper, a widely used metal in electrical wiring, exhibits excellent conductivity due to its metallic bonding. The ability of metals to be shaped and stretched without breaking, known as malleability and ductility, is also a result of the nature of metallic bonds. When a metal is deformed, the layers of atoms can slide past one another without disrupting the overall metallic bond, allowing the material to maintain its integrity. While covalent, canic, and metallic bonds represent the primary types of chemical bonding, it is essential to recognize that many compounds exhibit characteristics of more than one type of bond. For example, in compounds like sodium bicarbonate NaCOs, both ionic and covalent bonds are present. The sodium and bicarbonate ions are held together by ionic bonds, while the covalent bonds within the bicarbonate ion itself connect the carbon, oxygen, and hydrogen atoms. The interplay between different types of bonds also influences the properties of materials. For instance, the presence of covalent bonds in polymers gives them flexibility and resilience, while the ionic bonds in ceramics contribute to their hardness and brittleness. Understanding these relationships allows chemists to design and synthesize new materials with tailored properties for specific applications, ranging from pharmaceuticals to advanced materials used in technology. In summary, chemical bonds are the foundation of molecular and compound formation, dictating the relationships between atoms and influencing the properties of substances. Covalent bonds involve the sharing of electrons. Ionic bonds result from the transfer of electrons, and metallic bonds are characterized by a delocalized sea of electrons. Each type of bond contributes to the diverse array of materials and compounds we encounter in our daily lives, shaping the world around us. As we continue to explore the intricacies of chemical bonding, we gain a deeper appreciation for the connections that bind atoms together, revealing the underlying principles that govern the behavior of matter in all its forms. Bookmark message at the heart of chemistry lies a fundamental question: why do atoms bond? The answer to this question is intricately tied to the quest for stability, a driving force behind the formation of molecules and compounds. Atoms are inherently unstable when they possess incomplete outer electron shells, leading them to seek stability through various bonding interactions. This chapter explores the reasons behind atomic bonding, the energy dynamics involved, and the implications for the stability of matter. Atoms consist of a nucleus surrounded by electrons that occupy specific energy levels. The outermost electrons, known as valence electrons, play a crucial role in determining an atom's chemical behavior. Atoms strive to achieve a stable electron configuration, often resembling that of the nearest noble gas, which has a full outer shell. This drive for stability is the primary motivation for atoms to bond with one another, either by sharing, transferring, or pooling their electrons. The concept of energy is central to understanding atomic bonding. When atoms bond, they undergo changes in energy that can either release or absorb energy. The formation of a bond typically releases energy, resulting in a more stable arrangement of atoms. This release of energy occurs because the bonded state is lower in energy than the individual unbonded atoms. Conversely, breaking a bond requires an input of energy as it disrupts the stable arrangement of electrons. This energy dynamic is crucial in determining the stability of a compound and its reactivity. Covalent bonds, for instance, are formed when two atoms share electrons resulting in a more stable electron configuration for both. The energy released during the formation of a covalent bond is a reflection of the attractive forces between the positively charged nuclei and the negatively charged shared electrons. The strength of a covalent bond is influenced by the number of shared electron pairs. Double and triple bonds release more energy upon formation than single bonds, making them stronger and more stable. Ionic bonds, on the other hand, arise from the transfer of electrons between atoms, resulting in the formation of charged ions. The energy dynamics involved in ionic bonding are characterized by the lattice energy, which is the energy released when gaseous ions come together to form a solid ionic compound, K. This lattice energy is a measure of the strength of the ionic bond and is influenced by the charges of the ions and the distance between them. The greater the charge and the smaller the distance, the stronger the ionic bond and the more stable the resulting compound. Metallic bonds also contribute to the quest for stability, albeit in a different manner. In metals, atoms release some of their valence electrons, creating a sea of delocalized electrons that move freely throughout the metallic lattice. This delocalization allows for the sharing of electrons among many atoms, resulting in a stable arrangement that contributes to the unique properties of metals such as conductivity and malleability. The energy dynamics in metallic bonding are characterized by the balance between the attractive forces between the positively charged metal cations and the negatively charged sea of electrons. The quest for stability is not limited to individual atoms. It extends to the formation of molecules and compounds. When atoms bond, they often do so in specific ratios and arrangements that minimize energy and maximize stability. This is where the concept of resonance comes into play. In certain molecules, the arrangement of electrons can be represented by multiple valid Lewis structures, each depicting different bonding configurations. The true structure of the molecule is a hybrid of these resonance forms, reflecting the delocalization of electrons and contributing to the overall stability of the compound. Furthermore, stability of a compound is influenced by its environment. Factors such as temperature, pressure, and the presence of other substances can affect the energy dynamics of bonding. For example, increasing temperature can provide the energy needed to break bonds, leading to chemical reactions and changes in stability. Similarly, the presence of solvents can influence the solubility and stability of ionic compounds. As the interactions between ions and solvent molecules can either stabilize or destabilize the ionic lattice. The quest for stability also has implications for chemical reactions. During a reaction, bonds in the reactants must be broken before new bonds can form in the products. The energy required to break these bonds is known as the bond dissociation energy. If the energy released during the formation of new bonds in the products is greater than the energy required to break the bonds in the reactants, the reaction is exothermic and tends to proceed spontaneously. Conversely, if more energy is required to break the bonds than is released during the formation of new bonds, the reaction is endothermic and may require an external energy source to occur. In addition to the energy dynamics involved in bonding, the quest for stability is also influenced by the concept of electronegativity, which describes an atom's ability to attract electrons in a bond. Atoms with high electronegativity, such as fluorine and oxygen, tend to attract electrons more strongly, leading to polar covalent bonds where electrons are shared unequally. This polarity can affect the stability of molecules, as polar molecules often exhibit stronger intermolecular forces, such as hydrogen bonding, which can enhance their stability in certain environments. In summary, the quest for stability is a fundamental driving force behind atomic bonding. Atoms bond to achieve a stable electron configuration, and the energy dynamics involved in bond formation and breaking play a crucial role in determining the stability of compounds. Covalent, ionic, and metallic bonds each contributed to this quest in unique ways, influencing the properties and behaviors of matter. As we continue to explore the intricacies of chemical bonding and stability, we gain a deeper understanding of the forces that shape the world around us, revealing the underlying principles that govern the interactions of atoms and molecules. The quest for stability is not just a scientific inquiry. It is a journey that connects us to the very essence of matter and the universe itself. The hiss of a punctured cold pack releasing its frigid contents, the crackling warmth of a bonfire on a winter night, the gentle glow of fireflies illuminating a summer evening. These everyday phenomena all share one fundamental connection. They are visible manifestations of energy's pivotal role in chemical reactions. When atoms rearrange to form new substances, the dance of electrons between molecules is always accompanied by an intricate exchange of energy, following nature's immutable laws of thermodynamics. This energy transfer governs whether reactions will occur spontaneously or require external intervention, whether they will release heat to their surroundings or draw it in, and ultimately determines their practical applications in our world. Every chemical process involves bonds breaking and new bonds forming, each action demanding or releasing specific amounts of energy. Exothermic reactions, the generous givers of the chemical world, surrender their excess energy to the environment, often as heat or light. These are the reactions that power our lives in the most literal sense, from the combustion reactions fueling our vehicles to the metabolic processes sustaining our bodies. The flames of a candle represent millions of exothermic reactions occurring each second, where hydrocarbon molecules combine with oxygen to release energy in forms we can both see and feel. On an industrial scale, manufacturers harness these heat-releasing reactions to power everything from electricity generation to steel production. It's carefully controlling the energy output through reaction design and catalysts. Conversely, endothermic reactions behave as energy vampires, absorbing thermal energy from their surroundings to proceed. These cooling reactions surround us more often than we realize. The dissolution of ammonium nitrate in cold packs, the evaporation of sweat from our skin, even the photosynthesis process that sustains plant life. When a baker mixes baking soda with an acid in dough, the resulting endothermic reaction helps create air pockets while simultaneously cooling the mixture. Chemical cold packs used in sports medicine take advantage of this principle, providing immediate cooling through reactions that absorb considerable heat from injuries. In nature, endothermic processes regulate ecosystems from the phase changes, governing cloud formation to the chemical cycles maintaining ocean temperatures. The direction and feasibility of any reaction depends fundamentally on Gibbs free energy, the delicate balance between the system's enthalpy heat content, entropy disorder, and temperature. Spontaneous reactions will always proceed in the direction that lowers the system's overall free energy, regardless of whether they are exothermic or endothermic. This explains the counterintuitive reality that some reactions requiring energy input can still occur naturally if they result in sufficient increase in entropy. The dissolution of table salt in water provides a classic example where the modest energy required to break ionic bonds is outweighed by the entropy increase. As orderly solid crystals disperse into freely moving ions, nature frequently employs such entropy-driven reactions in biological systems, where molecular crowding and compartmentalization create environments where order, and disorder dance in carefully maintained balance. Activation energy forms the crucial barrier between reactants and products, the initial investment needed to start breaking bonds before new ones can form. This concept explains why paper doesn't spontaneously combust despite being capable of burning, or why hydrogen and oxygen can mix without reacting until the spark provides the necessary activation energy. Catalysts work their magic by providing alternative reaction pathways with lower activation energies, allowing reactions to proceed more quickly and at lower temperatures, a principle exploited in everything from catalytic converters to enzyme-driven biological processes. The platinum in automobile catalytic converters doesn't create or consume energy. It merely provides a surface where harmful exhaust gases can react more easily to form less toxic products. In biological systems, energy transfer and chemical reactions reaches extraordinary levels of sophistication. ATP molecules act as energy currency, their breakdown releasing just enough energy to power cellular processes while minimizing wasteful heat loss. Photosynthetic organisms perform the remarkable feat of capturing solar energy and converting it to chemical energy through precisely tuned reactions that minimize energy loss. The human body maintains a constant 98.6 degrees Fahrenheit temperature, largely through careful regulation of countless exothermic and endothermic metabolic reactions. Even our neural networks rely on meticulously balanced electrochemical gradients that require constant energy input to maintain, demonstrating how life exists in a perpetual state of controlled energetic imbalance. Industrial applications have learned to exploit the energy dynamics of reactions with increasing precision. Modern lithium-ion batteries operate through controlled exothermic and endothermic electrochemical reactions. It's carefully balanced to maximize energy, storage, and release. The Hopper process for ammonia synthesis demonstrates how understanding reaction energy profiles can feed the world by finding the perfect balance of temperature, pressure, and catalysts to overcome the reaction's significant activation barrier. Even household products like self-feeding coffee cans or instant cold packs demonstrate how clever packaging can separate reactants until the precise moment when their energy exchange is needed. Environmental implications of reaction energetics grow increasingly significant as we confront climate change. The combustion reactions powering our civilization release stored solar energy from fossilized biomass, but also produce greenhouse gases. Scientists now work to develop alternative reactions for energy storage and conversion that minimize environmental impact while maximizing efficiency, from hydrogen fuel cells to artificial photosynthesis. The challenge lies in finding reactions that are not only energetically favorable, but also sustainable at global scales. Carbon capture technologies aim to reverse the energetics of combustion, using carefully designed chemical processes to pull CO2 back out of the atmosphere, though these too must obey the fundamental laws of reaction thermodynamics. At the quantum level, the energy changes accompanying reactions stem from the rearrangement of electrons between discrete energy states. Spectroscopy techniques allow us to observe these transitions directly, measuring the precise energy differences between molecular orbitals as bonds break and form. Modern chemists use computational methods to map potential energy surfaces, predicting exactly how much energy will be released or absorbed during a reaction before conducting a single experiment. This predictive power underlies modern drug discovery, materials science, and renewable energy research, where synthesizing new compounds requires precise knowledge of the energetics involved. The study of reaction energetics continues to reveal profound insights about our universe's fundamental workings. From the nuclear fusion reactions powering stars to the delicate biochemical processes maintaining life, energy transfer remains the common thread connecting all chemical transformations. As we develop increasingly sophisticated ways to harness and manipulate these energy flows, we gain not just practical technologies, but a deeper appreciation for the elegant, energetic ballet underlying all matter in our universe. Every chemical reaction, whether in a distant galaxy or a laboratory beaker, follows these same universal principles, a reminder that energy is both the currency and the language of the chemical world. In the grand theater of chemistry, acids and bases take center stage, their interactions shaping the world around us in profound and often dramatic ways. These two classes of compounds, seemingly opposites, engage in a delicate dance that influences everything from the taste of our food to the pH of our blood. The properties and behaviors are not just academic curiosities. They are fundamental to the chemistry of life itself, acting as mood makers that can alter the environment and dictate the course of countless reactions. At the heart of the distinction between acids and bases lies the concept of protons. Acids are defined by their ability to donate protons, H ions, in a solution, while bases are characterized by their capacity to accept protons. This simple yet powerful interaction forms the basis of the Bronsted-Lowry theory, which elegantly captures the essence of acid-base chemistry. When an acid donates a proton, it transforms into its conjugate base, while the base that accepts the proton becomes its conjugate acid. This dynamic exchange is not merely a theoretical construct. It is a fundamental process that underpins many chemical reactions, influencing everything from metabolic pathways in our bodies to the behavior of substances in the environment. The properties of acids and bases are as varied as their applications. Acids, often characterized by their sour taste, can be found in a multitude of everyday substances. Citric acid gives lemons their tangy flavor, while acetic acid lends vinegar its sharpness. In the laboratory, strong acids like hydrochloric acid and sulfuric acid are powerful reagents capable of dissolving metals and reacting vigorously with bases. Their ability to donate protons makes them essential in various chemical processes, including the synthesis of fertilizers, pharmaceuticals, and even the digestion of food in our stomachs. On the other hand, bases are typically associated with a bitter taste and a slippery feel. Common examples include sodium hydroxide, found in drain cleaners, and baking soda, a staple in many kitchens. Bases work by accepting protons, and their interactions with acids can lead to neutralization reactions, where the two cancel each other out to form water and a salt. This reaction is not just a simple exchange. It is a fundamental process that plays a crucial role in maintaining the delicate balance of pH in biological systems. For instance, the bicarbonate buffer system in our blood helps regulate acidity, ensuring that our bodies function optimally. The pH scale, a logarithmic measure of hydrogen ion concentration, serves as a vital tool for understanding the behavior of acids and bases. Ranging from 0 to 14, the scale categorizes solutions as acidic pH 7, neutral pH equals 7, or basic pH greater than 7. This seemingly simple scale belies the complexity of acid-base chemistry, as even slight changes in pH can have significant effects on chemical reactions and biological processes. For example, the pH of our stomach acid hovers around 1.5 to 3.5, providing an optimal environment for digestive enzymes to break down food. In contrast, the pH of our blood is tightly regulated around 7.4, a narrow range that is crucial for maintaining homeostasis. The interactions between acids and bases are not limited to simple neutralization reactions. They can also lead to more complex phenomena. For instance, when an acid reacts with a metal, it can produce hydrogen gas, a reaction that is often accompanied by bubbling and fizzing. This is not just a laboratory curiosity. It has practical applications, such as in the production of hydrogen fuel. Similarly, the reaction between acids and carbonates produces carbon dioxide gas, a process that is harnessed in baking to create fluffy, leavened bread. In nature, acids and bases play pivotal roles in shaping ecosystems. The acidity of rainwater, influenced by atmospheric carbon dioxide and pollutants, can have profound effects on soil chemistry and aquatic environments. Acid rain, resulting from the dissolution of sulfur dioxide and nitrogen oxides in water, can lead to the leaching of essential nutrients from the soil and the acidification of lakes and rivers, threatening aquatic life. Conversely, the buffering capacity of natural waters can help mitigate these effects. demonstrating the intricate balance that exists in nature. As we explore the world of acids and bases, it becomes clear that their influence extends far beyond the confines of the laboratory. They are the mood makers of chemistry, capable of transforming environments, dictating reactions, and shaping the very fabric of life. From the sourness of a lemon to the bitterness of soap, the interactions of acids and bases are woven into the tapestry of our everyday experiences. Understanding their properties and behaviors not only enriches our knowledge of chemistry, but also deepens our appreciation for the delicate balance that sustains life on Earth. In conclusion, acids and bases are not merely chemical entities. They are dynamic participants in the ongoing drama of the natural world. Their ability to donate and accept protons, their diverse properties, and their interactions with one another and with the environment make them essential to the chemistry of life. As we continue our exploration of the atomic and molecular world, let us remember the vital roles that these mood makers play, shaping our experiences and influencing the reactions that define our existence in the intricate world of chemistry. In biology, the pH scale serves as a vital compass, guiding our understanding of acidity and basicity. This logarithmic scale, ranging from 0 to 14, provides a simple yet profound way to quantify the concentration of hydrogen ions H in a solution. The significance of pH extends far beyond the confines of the laboratory. It permeates our daily lives, influencing everything from the food we eat to the health of our ecosystems. Understanding the pH scale is essential for anyone seeking to grasp the fundamental principles of chemistry and the delicate balance of life at its core. pH scale is a measure of how acidic or basic a solution is. A pH of 7 is considered neutral, indicating a balance between hydrogen ions and hydroxide ions, while solutions with a pH less than 7 are classified as acidic, characterized by a higher concentration of hydrogen ions. Conversely, solutions with a pH greater than 7 are deemed basic or alkaline, possessing a higher concentration of hydroxide ions. This seemingly simple classification belies the complexity of acid-base chemistry, as even minor fluctuations in pH can have significant implications for chemical reactions and biological processes. The logarithmic nature of the pH scale means that each whole number change represents a tenfold difference in hydrogen ion concentration. For example, a solution with a pH of 4 is 10 times more acidic than one with a pH of 5, and 100 times more acidic than a solution with a pH of 6. This exponential relationship underscores the importance of pH in various contexts. Even slight changes can lead to dramatic shifts in chemical behavior. In biological systems, maintaining a stable pH is crucial for the proper functioning of enzymes, proteins, and metabolic pathways in the human body. For instance, pH of blood is tightly regulated around 7.4, a narrow range that is essential for maintaining homeostasis. Deviations from this optimal pH can have dire consequences. Acidosis, a condition characterized by an excess of hydrogen ions, can lead to symptoms such as confusion, fatigue, and even coma. Conversely, alkalosis, marked by deficiency of hydrogen ions, can result in muscle twitching, hand tremors, and other neurological disturbances. The body employs various buffering systems, such as the bicarbonate buffer system, to maintain this delicate balance, demonstrating the critical role of pH in health and disease. The importance of pH extends beyond human physiology. It is a key factor in environmental chemistry as well. The pH of soil affects nutrient availability for plants, influencing agricultural productivity and ecosystem health. Acidic soils with a pH below 6 can lead to nutrient leaching and hinder the growth of certain crops. Conversely, alkaline soils can limit the availability of essential minerals. Farmers and agronomists often test soil pH to determine the appropriate amendments needed to optimize crop yields. highlighting the practical applications of pH measurement in agriculture and aquatic environments. pH plays a crucial role in determining the health of ecosystems. Many aquatic organisms, including fish and amphibians, are sensitive to changes in pH. A drop in pH, often caused by acid rain or pollution, can lead to the acidification of lakes and rivers, threatening the survival of sensitive species. Coral reefs, which are vital to marine biodiversity, are also affected by ocean acidification, a phenomenon driven by increased carbon dioxide levels in the atmosphere. As the ocean absorbs more CO, it reacts with water to form carbonic acid, lowering the pH and disrupting the delicate balance of marine ecosystems. Measuring pH is a straightforward process, yet it requires precision and care. Various methods exist for determining pH, ranging from simple litmus paper tests to sophisticated electronic pH meters. Litmus paper, which changes color in response to acidity or basicity, provides a quick and easy way to gauge pH, though it lacks the accuracy of more advanced techniques. pH meters, on the other hand, utilize electrodes to measure the voltage difference between hydrogen ions in a solution and provide a precise pH reading. These instruments are invaluable in both laboratory and field settings, enabling scientists to monitor pH levels in various environments. In the realm of chemistry, the pH scale is not merely a tool for measurement. It is a gateway to understanding the behavior of acids and bases. The concept of pH is integral to the study of chemical reactions, as it influences reaction rates, equilibrium positions, and product formation. For instance, the rate of enzyme-catalyzed reactions is often pH dependent, with each enzyme exhibiting an optimal pH range for maximum activity. Understanding these relationships allows chemists and biologists to manipulate conditions to achieve desired outcomes. Whether in industrial processes or laboratory experiments, as we explore the pH scale, it becomes evident that its significance extends far beyond the realm of chemistry. It is a fundamental concept that permeates our understanding of biology, ecology, and environmental science. The delicate balance of pH influences the health of ecosystems, the productivity of agriculture, and the functioning of our own bodies. By measuring and monitoring pH, we gain insights into the intricate web of interactions that define life on Earth. In conclusion, the pH scale serves as a vital tool for measuring acidity and basicity, providing a framework for understanding the behavior of acids and bases in both chemical and biological contexts. Its importance cannot be overstated, as it influences everything from the health of our bodies to the vitality of our ecosystems. As we continue our exploration of the atomic and molecular world, let us appreciate the role of pH as a guiding principle, shaping our understanding of the chemistry of life and the delicate balance that sustains it. Water, the most abundant compound on Earth, is often referred to as the universal solvent, a title that reflects its unparalleled ability to dissolve a wide array of substances. This remarkable property stems from the unique structure of the water molecule itself, which consists of two hydrogen atoms covalently bonded to one oxygen atom, forming a bent shape. The arrangement of these atoms gives rise to a polar molecule with a partial negative charge near the oxygen atom and a partial positive charge near the hydrogen atoms. This polarity is the key to understanding water's extraordinary characteristics and its vital role in supporting life. One of the most significant properties of water is its ability to form hydrogen bonds. These weak attractions occur between the positively charged hydrogen atoms of one water molecule and the negatively charged oxygen atoms of neighboring water molecules. Although individually weak, these hydrogen bonds collectively confer remarkable strength and stability to water, leading to its unique physical properties. For instance, water has a high specific heat capacity, meaning it can absorb and retain large amounts of heat without undergoing significant temperature changes. This property is crucial for regulating temperatures in both the environment and living organisms. K. Allowing for stable conditions that support life. The high heat of vaporization of water is another critical aspect of its unique nature. When water evaporates, it requires a substantial amount of energy to break the hydrogen bonds that hold the molecules together. This property is essential for processes such as sweating in humans and transpiration in plants, where the evaporation of water helps to cool the body and regulate temperature. In this way, water acts as a natural coolant, maintaining homeostasis in living organisms and contributing to the overall balance of ecosystems. Water's role as a solvent is perhaps its most celebrated characteristic. Its polarity allows it to interact with various ionic and polar substances, effectively dissolving them. When an ionic compound, such as table salt, sodium chloride, is introduced to water, the positive sodium ions are attracted to the negative oxygen atoms of water, while the negative chloride ions are drawn to the positive hydrogen atoms. This interaction leads to the dissociation of the salt into its constituent ions, allowing them to disperse throughout the solution. This ability to dissolve a wide range of substances makes water an essential medium for chemical reactions, biological processes, and nutrient transport in living organisms. In biological systems, water serves as a crucial component of cells, constituting a significant portion of their mass. It acts as a solvent for biochemical reactions, facilitating the movement of ions, nutrients, and waste products. The cytoplasm of cells, primarily composed of water, provides a medium for metabolic processes, allowing enzymes and substrates to interact efficiently. Additionally, water plays a vital role in maintaining cell structure and function, as it helps to create turgor pressure in plant cells, supporting their rigidity and growth. The significance of water extends beyond its role as a solvent. Hay is also involved in various biochemical reactions. For instance, in photosynthesis, water molecules are split to release oxygen and provide electrons for the synthesis of glucose. Similarly, in cellular respiration, water is produced as a byproduct when glucose is metabolized for energy. These processes highlight the interconnectedness of water with the fundamental mechanisms of life, illustrating its importance in sustaining biological functions. Water's unique properties also contribute to the formation of habitats and ecosystems. The high surface tension of water, resulting from hydrogen bonding, allows certain organisms, such as water striders, to walk on its surface. This property also plays a role in the formation of droplets, which are essential for processes like precipitation and the distribution of water in the environment. Furthermore, the density of water is another fascinating aspect of its behavior. Unlike most substances, water expands when it freezes, causing ice to float on liquid water. This phenomenon creates an insulating layer on the surface of bodies of water, wanting life to survive beneath the ice during cold months. The significance of water extends to its role in climate regulation. The vast oceans, which cover more than 70% of the Earth's surface, act as a heat reservoir, absorbing and redistributing solar energy. This process helps to moderate global temperatures and influences weather patterns. The ability of water to store heat also plays a crucial role in the water cycle, where evaporation, condensation, and precipitation work together to maintain the balance of water on Earth. This cycle is essential for replenishing freshwater sources, supporting agriculture, and sustaining ecosystems. As we explore the water molecule, it becomes evident that its unique properties are not merely a result of chance. They are intricately linked to the very essence of life. Water's ability to dissolve, transport, and participate in biochemical reactions makes it indispensable for all living organisms. Its role as a temperature regulator, habitat creator, and climate moderator underscores its significance in shaping the world we inhabit. In conclusion, the water molecule stands as a testament to the beauty and complexity of nature. Its unique structure and properties enable it to play a central role in the chemistry of life. influencing everything from cellular processes to global climate patterns. As we continue our exploration of the molecular world, let us appreciate the profound impact of water, the substance that sustains life and connects us all. The world around us is a vibrant tapestry woven from various states of matter, each characterized by the arrangement and behavior of its constituent particles. From the solid ground beneath our feet to the air we breathe, matter exists in different forms, each with unique properties and behaviors. Understanding these state solids, liquids, gases, and plasma provides insight into the fundamental nature of the universe and the dynamic processes that govern it at the most basic level. Matter is composed of atoms and molecules, which are in constant motion. The state of matter is determined by the energy of these particles and the forces that hold them together. In solids, particles are tightly packed in a fixed arrangement, vibrating in place but unable to move freely. This close packing gives solids a definite shape and volume, making them rigid and stable. The strong intermolecular forces in solids, such as ionic or covalent bonds, keep the particles in their fixed positions, resulting in the characteristic hardness and incompressibility of solid materials. As we transition from solids to liquids, we witness a remarkable transformation. In liquids, particles are still closely packed, but they have gained enough energy to overcome some of the intermolecular forces that hold them in place. This allows the particles to slide past one another, giving liquids a definite volume but no fixed shape. Instead, liquids take the shape of their containers, flowing and adapting to their surroundings. The ability of liquids to flow is a crucial property that enables them to transport nutrients, waste, and other substances in biological systems. In industrial processes, the next state of matter, gases, represents a further increase in energy and particle movement. In gases, particles are widely spaced and move freely at high speeds, colliding with one another in the walls of their container. This rapid motion results in gases having neither a definite shape nor a fixed volume. They expand to fill any available space. The intermolecular forces in gases are minimal, allowing particles to move independently. This behavior is described by the kinetic molecular theory, which explains that the temperature of a gas is directly related to the average kinetic energy of its particles. As temperature increases, so does the energy of the particles, leading to more frequent and energetic collisions. Plasma, the fourth state of matter, is often referred to as the fourth state due to its unique properties. Plasma is formed when a gas is energized to the point that its atoms lose electrons, resulting in a collection of charged particles, including ions and free electrons. This state of matter is found in stars, including our Sun, for the extreme temperatures and pressures cause hydrogen and helium to exist in a plasma state. Plasma is also present in fluorescent lights and plasma TVs, where electrical energy excites gas particles, creating light. The behavior of plasma is governed by electromagnetic forces, making it distinct from the other states of matter. The transitions between these states of matter, known as phase changes, are fascinating processes that illustrate the dynamic nature of matter. When a solid is heated, its particles gain energy and begin to vibrate more vigorously. Once the energy surpasses a certain threshold, the solid melts, transforming into a liquid. This process, known as melting, occurs at a specific temperature called the melting point. Conversely, when a liquid is cooled, its particles lose energy and slow down, eventually forming a solid through the process of freezing. Similarly, when a liquid is heated, it can undergo evaporation, where particles at the surface gain enough energy to escape into the gas phase. This process occurs at any temperature, but it is more rapid at higher temperatures. When a liquid reaches its boiling point, it undergoes a more vigorous phase change known as boiling, where bubbles of gas form throughout the liquid. The transition from gas back to liquid is called condensation, a process that occurs when gas particles lose energy and come together to form a liquid. The transition from gas to plasma occurs when a gas is subjected to extreme energy, such as in lightning or the core of a star. Conversely, plasma can transition back to a gas when it loses energy and the charged particles recombine to form neutral atoms. These phase changes are not only fascinating from a scientific perspective, they have practical implications in various fields, including meteorology, engineering, environmental science. Understanding the states of matter and their transitions is essential for grasping the principles of thermodynamics, which govern energy transfer and transformation. The laws of thermodynamics describe how energy flows between systems and how it affects the behavior of matter. For example, the first law of thermodynamics states that energy cannot be created or destroyed, only transformed from one form to another. This principle is evident in the phase changes of matter, where energy is absorbed or released as particles. Transition between states. The study of states of matter also has profound implications for our understanding of the universe. The behavior of matter at different states is crucial for explaining phenomena such as the formation of stars, the behavior of gases in the atmosphere, and the properties of materials at extreme temperatures and pressures. For instance, the study of plasma physics has led to advancements in fusion energy research, which holds the potential for providing a nearly limitless source of clean energy. In conclusion, the states of matter, solids, liquids, gases, and plasma present the diverse forms that matter can take, each with its unique properties and behaviors. The transitions between these states illustrate the dynamic nature of matter and the energy changes that accompany them. Understanding these concepts is fundamental to the study of chemistry, physics, and biology, as they underpin the processes that govern the natural world. As we continue to explore the intricate dance of particles that make up our universe, we gain deeper insights into the fundamental principles that shape our reality. In the vast realm of chemistry, the concepts of mixtures and solutions play a pivotal role in our understanding of how substances interact and combine. These terms, often used interchangeably in everyday conversation, represent distinct categories of matter that exhibit unique properties and behaviors. From the air we breathe to the food we consume, mixtures and solutions are integral to our daily lives, influencing everything from taste to health. By exploring the characteristics of these combinations, we can gain a deeper appreciation for the chemistry that surrounds us at its core. A mixture is a physical combination of two or more substances that retain their individual properties. Unlike chemical compounds, which are formed through chemical reactions and result in new substances with distinct properties, mixtures can be separated into their original components through physical means. This characteristic is what makes mixtures so versatile and prevalent in nature. Common examples of mixtures include salad dressings, trail mix, and even the air we breathe, which is a blend of various gases. Mixtures can be classified into two main categories: homogeneous and heterogeneous. Homogeneous mixtures, also known as solutions, are uniform in composition and appearance. In these mixtures, the individual components are evenly distributed, making it difficult to distinguish one substance from another. A classic example of a homogeneous mixture is salt water, where salt dissolves completely in water, creating a solution that appears clear and consistent throughout. Other examples include vinegar, air, and alloys like bronze, which is a mixture of copper and tin. In contrast, heterogeneous mixtures consist of visibly different substances or phases. Components in a heterogeneous mixture are not uniformly distributed, allowing for the identification of individual parts. Examples of heterogeneous mixtures include salad, where the various ingredients can be seen and separated, and a mixture of sand and gravel, where the different particle sizes are easily distinguishable. The properties of heterogeneous mixtures can vary widely, depending on the proportions and characteristics of the individual components. One of the most fascinating aspects of mixtures is the concept of solutions. A solution is a specific type of homogeneous mixture formed when one substance, known as the solute, is dissolved in another substance called the solvent. The solvent is typically present in a larger amount, while the solute is present in a smaller quantity. The process of dissolving involves the interaction between the solute and solvent particles, leading to the formation of a uniform solution. Water is often referred to as the universal solvent due to its ability to dissolve a wide range of substances. This property is attributed to the polar nature of water molecules, which allows them to interact with various ionic and polar compounds. When sodium chloride is added to water, the positive sodium ions are attracted to the negative oxygen atoms of water, while the negative chloride ions are drawn to the positive hydrogen atoms. This interaction leads to the dissociation of the salt into its constituent ions, resulting in a clear saltwater solution. Solutions can vary in concentration, which refers to the amount of solute present in a given volume of solvent. Concentration can be expressed in several ways, including molarity, moles of solute per liter of solution, a mass percent mass of solute divided by the total mass of the solution, in parts per million ppm. Understanding concentration is crucial in various fields, including chemistry, biology, and environmental science, as it influences reaction rates, biological processes, and pollutant levels in ecosystems. In addition to solutions, mixtures can also include suspensions and colloids, which exhibit unique properties and behaviors. Suspensions are heterogeneous mixtures in which solid particles are dispersed throughout a liquid but are not dissolved. These particles are typically larger than those found in solutions and can settle over time if left undisturbed. A common example of a suspension is muddy water, where soil particles remain suspended in water but will eventually settle to the bottom if allowed to sit. Colloids, on the other hand, are mixtures where tiny particles are dispersed throughout a medium. But unlike suspensions, these particles do not settle out over time. Colloidal particles are larger than those in solutions, but smaller than those in suspensions, typically ranging from 1 nanometer to 1 micrometer in size. Colloids exhibit unique optical properties, such as the Tyndall effect, where light is scattered by the dispersed particles, making the colloid appear cloudy. Examples of colloids include milk, fog, and gelatin, each of which contains dispersed particles that contribute to i.e. distinct characteristics. The study of mixtures and solutions is not merely an academic exercise, It has practical implications in various fields, including medicine, food science, and environmental science. In medicine, understanding the properties of solutions is essential for formulating medications, intravenous fluids, and vaccines. The concentration of active ingredients must be carefully controlled to ensure efficacy and safety. In food science, the principles of mixtures and solutions are applied to create everything from emulsions in salad, dressings, to the carbonation in soft drinks. Environmental science also relies on the understanding of mixtures and solutions to address issues such as pollution and water quality. The ability to measure the concentration of pollutants in water or air is crucial for assessing environmental health and developing strategies for remediation. By understanding how different substances interact in mixtures, scientists can devise effective methods for cleaning up contaminated sites and protecting ecosystems. In conclusion, mixtures and solutions are fundamental concepts in chemistry that shape our understanding of the world around us. From the air we breathe to the food we eat, these combinations of substances influence our daily lives in countless ways. By exploring the properties and behaviors of mixtures, solutions, suspensions, and colloids, we gain valuable insights into the chemistry that underlies our existence. As we continue to delve into the intricacies of matter, let us appreciate the everyday chemistry that surrounds us, enriching our lives and shaping our understanding of the universe and the dynamic world of chemistry. The speed at which reactions occur can vary dramatically, influenced by a multitude of factors. Understanding reaction rates is crucial for chemists, as it allows them to control and optimize chemical processes in various applications, from industrial manufacturing to biological systems. The rate of a chemical reaction refers to the change in concentration of reactants or products over time, and it can be affected by several key factors, including temperature, concentration, surface area, and the presence of catalysts. By examining these factors, we can gain insights into the mechanisms of chemical reactions and the principles that govern them. One of the most significant factors affecting reaction rates is temperature. Increases the kinetic energy of the particles involved in the reaction also increases. This heightened energy leads to more frequent and energetic collisions between reactant molecules, which in turn increases the likelihood of successful reactions. According to the Arrhenius equation, the rate of a reaction is exponentially related to temperature. Even a small increase in temperature can lead to a substantial increase in reaction rate. For example, the rate of many chemical reactions can double with every 10 degrees Celsius rise in temperature. This principle is evident in everyday life, such as when cooking food. Higher temperatures accelerate the cooking process by increasing the rate of chemical reactions that occur in the ingredients. Concentration is another critical factor that influences reaction rates. In general, an increase in the concentration of reactants leads to a higher reaction rate. This is because a greater number of reactant molecules in a given volume results in more frequent collisions, increasing the chances of successful interactions. For instance, in a reaction between two gases, increasing the concentration of one or both reactants will lead to a faster reaction. This relationship is particularly important in industrial processes, where optimizing reactant concentrations can enhance production efficiency and yield. Surface area also plays a vital role in determining reaction rates, especially in reactions involving solids. When a solid reactant is involved, increasing its surface area allows for more collisions with other reactants. This can be achieved by grinding the solid into a powder or by breaking it into smaller pieces. For example, powdered sugar dissolves more quickly in water than granulated sugar due to its larger surface area, leading to a faster reaction with the solvent. This principle is crucial in various applications, including pharmaceuticals, where the rate of dissolution of solid drugs can significantly impact their effectiveness. The presence of catalysts is another important factor that can dramatically affect reaction rates. Catalysts are substances that increase the rate of a chemical reaction without being consumed in the process. They work by providing an alternative reaction pathway with a lower activation energy, allowing more reactant molecules to participate in the reaction. This means that even at lower temperatures, reactions can proceed at a faster rate when a catalyst is present. Enzymes, which are biological catalysts, play a crucial role in facilitating biochemical reactions in living organisms. For example, the enzyme catalyze speeds up the decomposition of hydrogen peroxide into water and oxygen, allowing this reaction to occur rapidly and efficiently in cells. In addition to these primary factors, other variables can also influence reaction rates. For instance, the pressure of gaseous reactants can affect reaction rates, particularly in reactions involving gases. Increasing the pressure effectively increases the concentration of gas molecules, leading to more frequent collisions and a higher reaction rate. This principle is particularly relevant in industrial processes involving gaseous reactants, such as the Hopper process for synthesizing ammonia. The study of reaction rates is not only important for understanding chemical processes, but also for practical applications in various fields. Environmental science, for example, understanding the rates of chemical reactions can help predict the behavior of pollutants in the atmosphere or water bodies. This knowledge is essential for developing strategies to mitigate environmental impacts and protect ecosystems. In the pharmaceutical industry, optimizing reaction rates is crucial for the efficient production of drugs. ensuring that they are manufactured safely and effectively. Moreover, the principles of reaction rates are fundamental to the field of kinetics, which explores the speed of chemical reactions and the factors that influence them. Kinetics provides valuable insights into the mechanisms of reactions, helping chemists understand how and why reactions occur. By studying reaction rates, scientists can develop models that predict the behavior of chemical systems under various conditions, leading to advancements in materials science, catechesis, and reaction engineering. In conclusion, the speed of chemical reactions is a complex interplay of various factors, including temperature, concentration, surface area, and the presence of catalysts. Understanding these factors is essential for controlling and optimizing chemical processes in both industrial and biological contexts. As we continue to explore the intricacies of reaction rates, we gain valuable insights into the fundamental principles of chemistry that govern the behavior of matter. By harnessing this knowledge, we can develop innovative solutions to challenges in fields ranging from environmental science to medicine, ultimately enhancing our understanding of the world around us. In the intricate world of chemistry, catalysts emerge as unsung heroes, playing a crucial role in accelerating reactions without being consumed in the process. These remarkable substances are essential in both industrial applications and biological systems, enabling reactions to occur at rates that would otherwise be impractically slow. By lowering the activation energy required for a reaction to proceed, catalysts facilitate the transformation of reactants into products, making them indispensable in various fields. From manufacturing to medicine, at the heart of a catalyst's function lies its ability to provide an alternative reaction pathway. Every chemical reaction has a certain energy barrier, known as activation energy, that must be overcome for the reaction to occur. This energy barrier represents the minimum energy required for reactant molecules to collide and form products. Catalysts work by stabilizing the transition state of a reaction, effectively lowering the activation energy and allowing more reacting molecules to participate in the reaction at a given temperature. This means that even at lower temperatures, reactions can proceed at a faster rate when a catalyst is present. Catalysts can be classified into two main categories: homogeneous and heterogeneous. Homogeneous catalysts exist in the same phase as the reactants, typically in a solution. Example of a homogeneous catalyst is sulfuric acid, which can catalyze the esterification reaction between an alcohol and a carboxylic acid. In this case, the catalyst is dissolved in the same liquid phase as the reactants, allowing for efficient interaction and reaction. Heterogeneous catalysts, on the other hand, exist in a different phase than the reactants, often as solids in contact with gaseous or liquid reactants. Classic example of a heterogeneous catalyst is platinum in catalytic converters, which facilitate the conversion of harmful gases from automobile exhaust into less harmful substances. In this scenario, the solid platinum provides a surface for the gas phase reactants to adsorb, allowing them to react more readily. The distinct phases of the catalyst and reactants can lead to unique reaction mechanisms and efficiencies. The role of catalysts extends beyond mere acceleration of reactions. They also play a significant part in determining the selectivity of reactions. Selectivity refers to the ability of a catalyst to favor the formation of one product over another in a reaction that can yield multiple products. This is particularly important in organic synthesis, where the desired product may be one of several possible outcomes. Catalysts can influence the reaction pathway, guiding reactants toward the formation of specific products while minimizing the formation of unwanted byproducts. This selectivity is crucial in the pharmaceutical industry, where the synthesis of complex molecules often requires precise control over reaction outcomes. Enzymes, which are biological catalysts, exemplify the remarkable efficiency and specificity of catalytic processes. Enzymes are proteins that facilitate biochemical reactions in living organisms, often operating under mild conditions of temperature and pressure. Each enzyme is highly specific to its substrate, the molecule upon which it acts, allowing for precise regulation of metabolic pathways. For example, the enzyme amylase catalyzes the breakdown of starch into sugars, while lactase facilitates the digestion of lactose. The efficiency of enzymes is a testament to the power of catalysis in biological systems, enabling life-sustaining reactions to occur rapidly and efficiently. The importance of catalysts in industrial processes cannot be overstated. Many chemical reactions used in manufacturing rely on catalysts to enhance efficiency and reduce energy consumption. For instance, the Haber process, which synthesizes ammonia from nitrogen and hydrogen, employs iron as a catalyst to increase the reaction rate. This process is vital for producing fertilizers that support global agriculture. Similarly, the production of sulfuric acid, one of the most widely used industrial chemicals, involves catalytic processes that optimize yield and minimize waste. Catalysts also play a crucial role in environmental chemistry. Catalytic converters in automobiles are designed to reduce harmful emissions by converting toxic gases, such as carbon monoxide and nitrogen oxides, into less harmful substances. By facilitating these reactions, catalysts help mitigate air pollution and improve air quality. Additionally, catalysts are employed in various processes for waste treatment and remediation, allowing for the breakdown of pollutants and the recovery of valuable resources. Despite their importance, catalysts are often overlooked in discussions about chemical reactions. Their ability to enhance reaction rates and selectivity makes them invaluable tools in both research and industry. However, the development of new and more efficient catalysts remains a significant area of research in chemistry. Scientists are continually exploring novel materials and approaches to catalysis, including the use of nanomaterials, biomimetic catalysts, and even artificial intelligence to design catalysts with tailored properties. The future of catalysis holds great promise, particularly in the context of sustainable chemistry, as the world faces challenges related to energy production, resource depletion, and environmental degradation. The development of efficient catalysts can contribute to more sustainable practices. For example, catalysts that facilitate the conversion of renewable feedstocks into valuable chemicals and fuels can help reduce reliance on fossil fuels and minimize carbon emissions. Additionally, catalysts that enable the efficient capture and conversion of carbon dioxide into useful products can play a vital role in addressing climate change. In conclusion, catalysts are the unsung heroes of chemistry, playing a vital role in accelerating reactions and enhancing selectivity. Their ability to lower activation energy and provide alternative reaction pathways makes them indispensable in both industrial and biological contexts. As we continue to explore the intricacies of catechesis, we gain valuable insights into the fundamental principles that govern chemical reactions. By harnessing the power of catalysts, we can develop innovative solutions to address the challenges of the modern world, paving the way for a more sustainable and efficient future. Biochemistry stands at the intersection of biology and chemistry, exploring the molecular mechanisms that underpin the processes of life. It delves into the structures and functions of biomolecules, including proteins, nucleic acids, and adenosine triphosphate, ATP, which are essential for the growth, development, and maintenance of living organisms. Understanding these molecules and their interactions is crucial for unraveling the complexities of biological systems and the biochemical pathways that sustain life. Proteins are one of the most diverse and vital classes of biomolecules. Composed of long chains of amino acids, proteins play a myriad of roles in biological systems, serving as enzymes, structural components, transporters, and signaling molecules. The sequence of amino acids in a protein, known as its primary structure, determines its unique three-dimensional shape, which is critical for its function. This relationship between structure and function is a fundamental principle in biochemistry, as even slight changes in a protein's structure can significantly impact its activity. Enzymes, a specific type of protein, act as biological catalysts, accelerating chemical reactions within cells. They lower the activation energy required for reactions to occur, allowing metabolic processes to proceed at rates compatible with life. Each enzyme is highly specific, typically catalyzing only one type of reaction or acting on a particular substrate. For example, the enzyme lactase breaks down lactose into glucose and galactose, facilitating the digestion of dairy products. The efficiency and specificity of enzymes are essential for maintaining metabolic balance and regulating biochemical pathways. The regulation of enzyme activity is a critical aspect of cellular function. Enzymes can be activated or inhibited by various factors, including the concentration of substrates, presence of inhibitors, and environmental conditions such as pH and temperature. Feedback inhibition is a common regulatory mechanism in which the end product of a metabolic pathway inhibits an earlier step, preventing the overproduction of that product. This intricate regulation ensures that cells maintain homeostasis and respond appropriately to changes in their environment. Nucleic acids, including deoxyribone nucleic acid DNA and ribonucleic acid RNA, are another essential class of biomolecules in biochemistry. DNA serves as the genetic blueprint for all living organisms, coding the information necessary for the development, functioning, and reproduction of cells. The structure of DNA is characterized by a double helix formed by two complementary strands of nucleotides, which are composed of a sugar, a phosphate group, and a nitrogenous base. The sequence of these bases of adenine, thymine, cytosine, guanine, and guanidine determines the genetic information carried by the DNA molecule. The process of DNA replication is fundamental to cellular division and inheritance. During replication, the double helix unwinds, and each strand serves as a template for the synthesis of a new complementary strand. This process ensures that genetic information is accurately passed on to daughter cells, maintaining the continuity of life. Additionally, DNA is involved in the synthesis of RNA through a process called transcription, where a specific segment of DNA is copied into messenger RNA, mRNA. This mRNA then serves as a template for protein synthesis during translation, linking the genetic code to the production of proteins. ATP, or adenosine triphosphate, is often referred to as the energy currency of the cell. It is a nucleotide composed of adenine, ribose, and 3 phosphate groups. The high energy bonds between the phosphate groups store potential energy, which can be released when ATP is hydrolyzed to adenosine diphosphate, ATP, and inorganic phosphate. This energy release powers various cellular processes, including muscle contraction, active transport, and biosynthesis. The production of ATP occurs primarily through cellular respiration, a series of metabolic pathways that convert glucose and other organic molecules into usable energy. Glycolysis, the citric acid cycle, and oxidative phosphorylation are key stages in this process, each contributing to the generation of ATP. In addition to cellular respiration, ATP is also produced during photosynthesis in plants, where light energy is converted into chemical energy stored in glucose molecules. The interplay between proteins, nucleic acids, and ATP is fundamental to the functioning of living organisms. Proteins carry out the majority of cellular functions, while nucleic acids store and transmit genetic information. ATP serves as the energy source that drives biochemical reactions, enabling cells to perform work and maintain homeostasis. The T's intricate network of interactions highlights the complexity of life at the molecular level. and underscores the importance of biochemistry in understanding biological processes. Biochemistry also plays a crucial role in medicine and biotechnology. Advances in our understanding of biomolecules have led to the development of targeted therapies, vaccines, and diagnostic tools. For example, the discovery of enzymes involved in specific metabolic pathways has paved the way for enzyme replacement therapies in genetic disorders. Additionally, the ability to manipulate DNA through techniques such as CRISPR-Cas9 has revolutionized genetic engineering, allowing for precise modifications to the genetic code. Furthermore, biochemistry is essential for understanding the molecular basis of diseases. Many diseases, including cancer, diabetes, and neurodegenerative disorders, are linked to disruptions in biochemical pathways. By studying the underlying biochemical mechanisms, researchers can identify potential targets for therapeutic intervention and develop strategies for prevention and treatment. Metabolism is the sum of all chemical reactions that occur within a living organism, encompassing the processes that convert food into energy and the building blocks necessary for growth and maintenance. It is a complex network of metabolic pathways that can be broadly categorized into two main types, catabolism and anabolism. These two processes work in tandem to maintain the delicate balance of energy and matter within cells, ensuring that organisms can thrive in their environments. Catabolism refers to the set of metabolic pathways that break down molecules to release energy. This process typically involves the degradation of complex organic compounds, such as carbohydrates, fats, and proteins, into simpler molecules. The energy release during catabolic reactions is captured in the form of adenosine triphosphate, ATP, which serves as the primary energy currency of the cell. For example, during cellular respiration, glucose is oxidized through a series of enzymatic reactions, ultimately producing ATP, carbon dioxide, and water. This process not only provides energy for cellular activities, but also generates the building blocks needed for anabolic pathways. Anabolism, on the other hand, encompasses the metabolic pathways that construct complex molecules from simpler ones. This process requires an input of energy, often derived from the ATP produced during catabolism. Metabolic reactions are essential for growth, repair, and maintenance of cellular structures. For instance, the synthesis of proteins from amino acids, the formation of nucleic acids from nucleotides, and the assembly of polysaccharides from simple sugars are all examples of anabolic processes. These reactions are vital for the development of tissues, the production of enzymes, the overall functioning of living organisms. The interplay between catabolism and anabolism is crucial for maintaining metabolic homeostasis. This balance ensures that energy production and consumption are finely tuned to meet the needs of the organism. When energy intake exceeds energy expenditure, the excess energy is stored in the form of glycogen or fat, providing a reserve for times of need. Conversely, when energy intake is insufficient, the body can mobilize these stored reserves to meet its energy demands. This dynamic equilibrium is essential for survival, allowing organisms to adapt to changing environmental conditions and energy availability. Metabolic pathways are often organized into interconnected networks, with various enzymes facilitating the conversion of substrates into products. Each step in a metabolic pathway is catalyzed by a specific enzyme, which lowers the activation energy required for the reaction to occur. Enzymes are highly regulated, ensuring that metabolic pathways operate efficiently and respond to the needs of the cell. For example, the availability of substrates, the presence of inhibitors or activators, and changes in environmental conditions can all influence enzyme activity and, consequently, the rate of metabolic reactions. One of the key regulatory mechanisms in metabolism is feedback inhibition, where the end product of a metabolic pathway inhibits an earlier step in the pathway. K. This process prevents the overproduction of a particular metabolite and helps maintain homeostasis. For instance, in the synthesis of the amino acid isoleucine from threonine. The accumulation of isoleucine can inhibit the activity of the enzyme threonine deaminase, thereby regulating its own production. This type of regulation is essential for ensuring that metabolic pathways operate efficiently and that resources are allocated appropriately. Metabolism is also influenced by external factors, including diet, exercise, and hormonal regulation. The nutrients we consume provide the substrates for catabolic and anabolic reactions, and the balance of macronutrients, carbohydrates, proteins, and fats can significantly impact metabolic processes. For example, a diet high in carbohydrates can promote the storage of glycogen, while a diet rich in proteins can enhance muscle synthesis through anabolic pathways. Additionally, physical activity increases energy expenditure, stimulating catabolic processes to meet the heightened energy demands of the body. Hormones play a critical role in regulating metabolism, acting as signaling molecules that coordinate metabolic pathways in response to changes in the internal and external environment. Insulin and glucagon are two key hormones involved in glucose metabolism. Insulin, produced by the pancreas, promotes the uptake of glucose by cells and stimulates the synthesis of glycogen and fat. In contrast, glucagon stimulates the breakdown of glycogen into glucose and the mobilization of fatty acids for energy production. The balance between these hormones is essential for maintaining blood glucose levels and overall metabolic homeostasis. In addition to these regulatory mechanisms, metabolic pathways are also subject to genetic control. Genes encode the enzymes that catalyze metabolic reactions, and variations in these genes can influence metabolic efficiency and susceptibility to diseases. For example, genetic mutations affecting enzymes involved in metabolic pathways can lead to inherited metabolic disorders, such as phenylketonuria, PKU, or galactosemia. Understanding the genetic basis of metabolism is crucial for developing targeted therapies and interventions for these conditions. The study of metabolism extends beyond individual organisms. It also encompasses ecological and evolutionary perspectives. Metabolic rates can vary significantly among different species, influencing their energy requirements and ecological niches. For instance, endothermic animals, such as mammals and birds, have higher metabolic rates than ectothermic animals, such as reptiles and amphibians. This difference in metabolism affects their behavior, habitat preferences, and interactions with other organisms in their ecosystems. In conclusion, metabolism is the energy of life, encompassing the intricate balance between catabolism and anabolism. Through a complex network of metabolic pathways, organisms convert food into energy and build the molecules necessary for growth and maintenance. The regulation of these pathways is essential for maintaining metabolic homeostasis, allowing organisms to adapt to changing conditions and energy availability. As we continue to explore the intricacies of metabolism, we gain valuable insights into the fundamental processes that sustain life, paving the way for advancements in medicine, nutrition, and environmental science. By understanding the chemistry of metabolism, we can unlock the secrets of energy production and utilization, ultimately enhancing our knowledge of the pH. Chemistry is the branch of science that explores the chemical composition of the earth and the processes that govern the interactions of its materials. It encompasses a wide range of phenomena, from the formation of minerals and rocks to the cycling of elements through the atmosphere, hydrosphere, lithosphere, and biosphere. Understanding geochemical processes is essential for deciphering the Earth's history, its current state, and the dynamics that shape its future. Among the myriad of geochemical processes, weathering and the carbon cycle stand out as fundamental mechanisms that influence the Earth's surface and its climate. Weathering is the process by which rocks and minerals are broken down into smaller particles through physical, chemical, and biological means. This process is crucial for soil formation and the cycling of nutrients, as it transforms solid rock into the loose material that supports plant life. Physical weathering involves the mechanical breakdown of rocks without altering their chemical composition. Factors such as temperature fluctuations, freeze-thaw cycles, and the action of wind and water contribute to this type of weathering. For instance, when water seeps into cracks in rocks and freezes, it expands, exerting pressure on the surrounding rock and causing it to fracture. Chemical weathering, on the other hand, involves the alteration of the chemical composition of minerals. This process occurs when minerals react with water, acids, or other chemicals in the environment. For example, feldspar, a common mineral in granite, can undergo hydrolysis, a chemical reaction with water that transforms it into clay minerals. This transformation not only contributes to soil formation, but also releases essential nutrients, such as potassium and sodium, into the soil, making them available for plant uptake. Biological weathering is another important aspect of the weathering process, where living organisms contribute to the breakdown of rocks and minerals. Plant roots can penetrate cracks in rocks, exerting pressure and facilitating physical weathering. Additionally, certain fungi and bacteria produce organic acids that can chemically alter minerals, further enhancing the weathering process. The interplay between physical, chemical, and biological weathering creates a dynamic environment that shapes the Earth's surface and influences the distribution of nutrients. The carbon cycle is a critical geochemical process that regulates the flow of carbon through the Earth's systems. Carbon is an essential element for life, forming the backbone of organic molecules such as carbohydrates, proteins, and nucleic acids. The carbon cycle involves several key processes, including photosynthesis, respiration, decomposition, and the exchange of carbon between the atmosphere, oceans, and terrestrial ecosystems. Photosynthesis is the process by which plants, algae, and some bacteria convert carbon dioxide from the atmosphere into organic matter using sunlight. During this process, carbon dioxide is absorbed through small openings in plant leaves called stomata, and in the presence of sunlight, it is transformed into glucose and oxygen. This process not only provides energy for the plants themselves, but also serves as the foundation of the food chain, as herbivores consume plants and carnivores consume herbivores. Respiration is the reverse process of photosynthesis, where organisms break down organic matter to release energy. During respiration, carbon dioxide is produced as a byproduct and returned to the atmosphere. This continuous exchange of carbon between photosynthesis and respiration maintains a balance in the carbon cycle, ensuring that carbon is cycled through living organisms and the environment. Decomposition is another vital process in the carbon cycle, where dead organic matter is broken down by microorganisms, fungi, and detritivores. This process releases carbon back into the soil and atmosphere, contributing to the overall carbon balance. Decomposers play a crucial role in recycling nutrients and ensuring the availability of essential elements for new plant growth. The oceans also play a significant role in the carbon cycle, acting as both the source and sink for carbon dioxide. Carbon dioxide from the atmosphere dissolves in seawater, where it can be utilized by marine organisms for photosynthesis. Additionally, the oceans absorb a substantial amount of carbon dioxide, helping to regulate atmospheric levels. However, increased carbon emissions from human activities, such as burning fossil fuels and deforestation, have led to higher concentrations of carbon dioxide in the atmosphere, contributing to climate change and ocean acidification. GEOCHEMICAL. Processes are not isolated. They are interconnected and influence one another in complex ways. For example, weathering contributes to the carbon cycle by releasing minerals that can react with carbon dioxide, forming carbonates that sequester carbon in the lithosphere. This process is particularly important in regulating long-term carbon levels in the atmosphere and mitigating climate change. The study of geochemistry also extends to understanding the impact of human activities on the Earth's chemical processes. Industrialization, urbanization, and agricultural practices have altered natural geochemical cycles, leading to environmental challenges such as soil degradation, water pollution, and climate change. For instance, the excessive use of fertilizers in agriculture can lead to nutrient runoff, causing eutrophication in water bodies and disrupting aquatic ecosystems. Moreover, the extraction and combustion of fossil fuels release significant amounts of carbon dioxide and other greenhouse gases into the atmosphere, exacerbating global warming. Understanding these geochemical processes is crucial for developing sustainable practices that minimize environmental impact and promote the health of ecosystems. In conclusion, geochemistry encompasses a wide range of chemical processes that shape the Earth and its environment. Weathering and the carbon cycle are two fundamental processes that illustrate the dynamic interactions between the Earth's materials and the living organisms that inhabit it. By studying these processes, we gain valuable insights into the Earth's history, its current state, and the challenges it faces in the context of human activities. As we continue to explore the intricate web of geochemical interactions, we can better understand the delicate balance that sustains life on our planet and the importance of preserving it for future generations. The atmosphere is a complex and dynamic mixture of gases that envelops the Earth, playing a crucial role in sustaining life and regulating the planet's climate. Understanding the chemical composition of the atmosphere is essential for grasping how it influences weather patterns, climate change, and the overall health of our environment. The atmosphere is primarily composed of nitrogen, approximately 78%, oxygen, about 21%, and trace amounts of other gases, including argon, carbon dioxide, methane, and water vapor. Each of these components contributes to the intricate balance that governs atmospheric processes. Nitrogen, the most abundant gas in the atmosphere, is relatively inert and does not readily react with other substances. This stability allows nitrogen to serve as a filler gas, providing volume to the atmosphere without significantly affecting its chemical reactivity. Oxygen, on the other hand, is vital for life as it is essential for respiration in most living organisms. The presence of oxygen in the atmosphere is a result of photosynthesis, a process carried out by plants, algae, and some bacteria that convert carbon dioxide and sunlight into organic matter and oxygen. This delicate balance between oxygen production and consumption is fundamental to maintaining life on Earth. Carbon dioxide, although constituting only about 0.04% of the atmosphere, plays a critical role in regulating the Earth's climate. It is a greenhouse gas, meaning it has the ability to trap heat in the atmosphere. This property is essential for maintaining the Earth's temperature, as it prevents excessive heat from escaping into space. However, human activities, particularly the burning of fossil fuels and deforestation, have led to a significant increase in carbon dioxide concentrations in the atmosphere. This rise in greenhouse gases is a primary driver of climate change, resulting in global warming and associated impacts such as rising sea levels, altered weather patterns, and increased frequency of extreme weather events. Methane is another potent greenhouse gas with a much higher heat-trapping ability than carbon dioxide, although it is present in smaller quantities. Methane is released during the production and transport of coal, oil, and natural gas, as well as from livestock and other agricultural practices. The increase in methane emissions has raised concerns about its contribution to climate change, as it can remain in the atmosphere for a shorter duration than carbon dioxide, but is significantly more effective at trapping heat during that time. Water vapor is a unique component of the atmosphere, as it is the only gas that can exist in all three states of matter: solid, liquid, and gas within the Earth's temperature range. Water vapor plays a crucial role in the Earth's climate system, as it is a key driver of weather patterns and influences the formation of clouds and precipitation. The amount of water vapor in the atmosphere varies significantly depending on temperature and humidity levels. Warmer air can hold more moisture, leading to increased evaporation and, consequently, more water vapor in the atmosphere. This feedback loop can amplify the effects of climate change, as higher temperatures lead to more water vapor, which in turn enhances the greenhouse effect. The chemical composition of the atmosphere is not static. It is influenced by various natural and anthropogenic processes. Volcanic eruptions, for example, can release large amounts of ash and gases, including sulfur dioxide, into the atmosphere. Sulfur dioxide can react with water vapor to form sulfuric acid, contributing to acid rain, which can have detrimental effects on ecosystems, water quality, and human health. Additionally, natural phenomena such as wildfires and dust storms can introduce particulate matter and other pollutants into the atmosphere, affecting air quality and climate. Human activities have significantly altered the composition of the atmosphere, leading to environmental challenges that require urgent attention. The burning of fossil fuels for energy, transportation, industrial processes releases not only carbon dioxide, but also a range of other pollutants, including nitrogen oxides, sulfur oxides, and particulate matter. These pollutants can contribute to the formation of smog, respiratory problems, and other health issues. The interaction between these pollutants and atmospheric chemistry can lead to complex reactions that produce secondary pollutants, as ozone, which can be harmful to both human health and the environment. Ozone is a unique component of the atmosphere, as it exists in two distinct layers. In the stratosphere, ozone forms the ozone layer, which protects life on Earth by absorbing the majority of the sun's harmful ultraviolet UV radiation. However, at ground level, ozone is a harmful pollutant that can cause respiratory problems and damage crops and other vegetation. The formation of ground-level ozone is a result of chemical reactions between nitrogen oxides and volatile organic compounds in the presence of sunlight. This highlights the importance of understanding atmospheric chemistry in addressing air quality issues and protecting public health. The effects of atmospheric chemistry extend beyond local air quality. They have global implications for climate change and environmental sustainability. The increase in greenhouse gases, particularly carbon dioxide and methane, has led to a rise in global temperatures, resulting in a cascade of effects on ecosystems, weather patterns, and human societies. Climate change is associated with more frequent and intense heat waves, droughts, floods, and storms, posing significant challenges for agriculture, water resources, and public health. To mitigate the impacts of climate change, it is essential to reduce greenhouse gas emissions and transition to more sustainable practices. This includes adopting renewable energy sources, improving energy efficiency, and promoting sustainable land use practices. Additionally, protecting and restoring natural ecosystems such as forests and wetlands can enhance carbon sequestration and help regulate the atmospheric composition. Understanding atmospheric chemistry is crucial for developing effective policies and strategies to address climate change and air quality issues. Monitoring the composition of the atmosphere and studying the interactions between different gases and pollutants can provide valuable insights into the processes driving climate change and inform decision-making at local, national, and global levels. In conclusion, atmospheric chemistry is a vital field of study that examines the chemical composition of the air we breathe and its effects on climate and the environment. The interactions between gases, pollutants, and natural processes shape the Earth's climate system and influence weather patterns, air quality, and public health. As we face the challenges of climate change and environmental degradation, a deeper understanding of atmospheric chemistry will be essential for developing sustainable solutions that protect both the planet and its inhabitants. by addressing the complexities of the atmosphere and its chemical processes, we can work towards a healthier, more sustainable future for generations to come. Cosmic chemistry is a fascinating field that delves into the chemical processes occurring in the vast expanse of space. It encompasses the formation of elements, the life cycle of stars, and the intricate interactions that give rise to the universe's diverse array of materials. Understanding cosmic chemistry not only sheds light on the origins of the elements that make up our world, but also provides insights into the fundamental processes that govern the universe. The story of cosmic chemistry begins with the Big Bang, the event that marked the birth of the universe approximately 13.8 billion years ago. In the moments following the Big Bang, the universe was an incredibly hot and dense environment, primarily composed of fundamental particles such as quarks and electrons. As the universe expanded and cooled, these particles began to combine, forming protons and neutrons. Within just a few minutes, the first light elements, hydrogen, helium, and trace amounts of lithium and beryllium, were created through a process known as Big Bang nucleosynthesis. This primordial nucleosynthesis set the stage for the chemical evolution of the universe. Hydrogen, the simplest and most abundant element, constitutes about 75% of the universe's normal matter. Helium follows as the second most abundant element, making up about 25%. The remaining elements, including heavier ones like carbon, oxygen, and iron, were formed later through stellar processes. The formation of these heavier elements occurs primarily within stars, where the extreme temperatures and pressures create the conditions necessary for nuclear fusion. Stars are the cosmic furnaces where elements are synthesized. The life cycle of a star begins with the gravitational collapse of a cloud of gas and dust, primarily composed of hydrogen. As the cloud collapses, it heats up, and when the core temperature reaches approximately 10 million degrees Celsius, nuclear fusion ignites. In this process, hydrogen nuclei protons fuse to form helium, releasing vast amounts of energy in the form of light and heat. This energy is what powers stars and allows them to shine. As stars evolve, they undergo various stages of fusion, creating heavier elements in the process. In more massive stars, once hydrogen is depleted in the core, the star begins to fuse helium into heavier elements such as carbon and oxygen. This process continues, with the star fusing progressively heavier elements until it reaches iron. Iron is unique in that it has the highest binding energy per nucleon, meaning that fusing iron does not release energy. Instead, it requires energy. This leads to a critical point in a star's life cycle. When a massive star exhausts its nuclear fuel, it can no longer support itself against gravitational collapse. The core collapses, leading to a supernova explosion, one of the most energetic events in the universe. During this explosion, the intense heat and pressure allow for rapid nucleosynthesis, creating a wide array of elements, including those heavier than iron, such as gold, silver, and uranium. These newly formed elements are then ejected into space, enriching the interstellar medium with the building blocks for future stars, planets, and even life. The remnants of supernova explosions contribute to the formation of new stars and planetary systems. The ejected material mixes with surrounding gas and dust, forming dense regions that can collapse under their own gravity to create new stars. This cycle of stellar birth, evolution, and death is a fundamental aspect of cosmic chemistry, illustrating how elements are continuously recycled throughout the universe. In addition to supernova, other processes contribute to the creation of elements in space. For instance, neutron capture processes, such as the S process, slow neutron capture, and R process, rapid neutron capture, occur in different stellar environments. The S process takes place in asymptotic giant branch stars, where neutrons are captured slowly, allowing for the formation of stable isotopes. The art process, on the other hand, occurs in explosive environments, such as supernova or neutron star mergers, where neutrons are captured rapidly, leading to the creation of heavy, stable isotopes. The study of cosmic chemistry extends beyond the formation of elements. It also encompasses the chemical composition of celestial bodies. Observations of stars, planets, and interstellar clouds reveal a rich tapestry of molecules and compounds. For example, complex organic molecules, including amino acids and sugars, have been detected in the gas and dust surrounding young stars. These findings suggest that the building blocks of life may be synthesized in space and delivered to planets through processes such as comet impacts. The exploration of cosmic chemistry has been greatly enhanced by advancements in observational technology. Scopes equipped with spectrometers allow scientists to analyze the light emitted or absorbed by celestial objects, revealing their chemical composition. By studying the spectra of stars and galaxies, researchers can identify the presence of specific elements and molecules, providing valuable insights into the processes occurring in distant regions of the universe. One of the most significant discoveries in cosmic chemistry is the detection of water in various forms throughout the universe. Water vapor has been found in the atmospheres of exoplanets, in the icy bodies of the Kuiper Belt, and even in the plumes of water erupting from moons like Europa and Enceladus. The presence of water is a key indicator of potential habitability, as it is essential for life as we know it. The study of cosmic chemistry also raises intriguing questions about the origins of life on Earth. Theories such as panspermia propose that life may have originated from microorganisms or organic compounds that were transported to Earth via comets or meteorites. The discovery of organic molecules in space supports this idea, suggesting that the ingredients for life may be widespread throughout the universe as we continue to explore the cosmos. The field of cosmic chemistry will undoubtedly expand our understanding of the universe and our place within it. The ongoing search for exoplanets and the study of their atmospheres will provide further insights into the chemical processes that govern planetary formation and the potential for life beyond Earth. Additionally, advancements in space missions, such as sample return missions to asteroids and comets, will allow scientists to analyze the chemical composition of these celestial bodies directly, shedding light on the origins of the solar system. In conclusion, cosmic chemistry is a captivating field that explores the chemical processes occurring in space. From the formation of elements in stars to the complex interactions that shape the universe, the life cycle of stars, the synthesis of heavy elements during supernova, and the detection of organic molecules in interstellar clouds all contribute to our understanding of the cosmos. As we continue to unravel the mysteries of cosmic chemistry, we gain valuable insights into the origins of the elements that make up our world and the potential for life beyond our planet. The universe is a vast and dynamic laboratory, and the study of its chemistry will continue to inspire curiosity and wonder for generations to come. Chemistry is often viewed as a collection of distinct disciplines, each focusing on specific aspects of matter and its interactions. However, a deeper examination reveals that all branches of chemistry are intricately interconnected, forming a cohesive framework that underpins our understanding of the natural world. From the microscopic interactions of atoms and molecules to the vast cosmic processes that shape the universe, the interconnectedness of chemistry is a testament to the unity of scientific inquiry. At the microscopic level, chemistry begins with the behavior of atoms and molecules. The interactions between these fundamental particles govern the properties of matter and dictate how substances combine and react. For instance, the formation of chemical bonds with a covalent ionic or metallic depends on the arrangement of electrons in the outer shells of atoms. Its electron configuration not only determines an element's reactivity, but also influences its physical properties, such as boiling and melting points, solubility, and conductivity. Understanding these atomic interactions is essential for grasping the principles of chemical reactions and the behavior of materials. As we move from the microscopic to the macroscopic scale, the interconnectedness of chemistry becomes even more apparent. The principles of thermodynamics, which govern energy, transfer, and transformation, play a crucial role in chemical reactions. The laws of thermodynamics dictate how energy is conserved, how it flows between systems, and how it influences the spontaneity of reactions. For example, exothermic reactions release energy, often in the form of heat, while endothermic reactions absorb energy from their surroundings. This interplay between energy and matter is fundamental to understanding not only chemical processes, but also biological systems, environmental phenomena, and industrial applications. In biological chemistry or biochemistry, the interconnectedness of chemistry is exemplified by the complex networks of metabolic pathways that sustain life. These pathways involve a series of chemical reactions that convert nutrients into energy, synthesize essential biomolecules, and regulate cellular functions. Enzymes, which are biological catalysts, facilitate these reactions by lowering the activation energy required for them to occur. The specificity of enzyme-substrate interactions is a prime example of how molecular structure and function are intertwined, teaching the importance of chemistry in understanding biological processes. The interconnectedness of chemistry extends beyond individual reactions to encompass entire ecosystems. The cycling of elements, such as carbon, nitrogen, and phosphorus, illustrates how chemical processes are linked across different environmental compartments. For instance, the carbon cycle involves the exchange of carbon between the atmosphere, oceans, soil, and living organisms. Photosynthesis, respiration, decomposition, decay, and combustion are all interconnected processes that contribute to the cycling of carbon, influencing climate, weather patterns, and the health of ecosystems. Understanding these cycles is essential for addressing environmental challenges such as climate change and nutrient pollution. In addition to the biological and environmental aspects, the connectedness of chemistry is evident in the field of materials science. The development of new materials, such as polymers, nanomaterials, and composites, relies on a deep understanding of chemical principles. The properties of materials are determined by their molecular structure and the interactions between their constituent atoms. For example, strength and flexibility of a polymer depend on the arrangement of its monomers and the types of chemical bonds that hold them together. Advances in materials science have led to innovations in various fields, including electronics, medicine, and energy storage, demonstrating how chemistry drives technological progress. The cosmic scale of chemistry further emphasizes its interconnectedness, the processes that govern the formation of elements in stars, the synthesis of complex molecules in interstellar space, and the chemical reactions that occur on planetary surfaces are all part of a grand tapestry of cosmic chemistry. The elements created in stars are recycled through supernova explosions, enriching the interstellar medium and contributing to the formation of new stars and planets. This cycle of stellar birth, evolution, and death illustrates how chemistry operates on a universal scale, connecting the microscopic interactions of atoms to the vast structures of galaxies. Moreover, the study of cosmic chemistry raises profound questions about the origins of life and the potential for life beyond Earth. The discovery of organic molecules in space, such as amino acids and simple sugars, suggest that the building blocks of life may be widespread throughout the universe. This interconnectedness between chemistry and the search for extraterrestrial life highlights the importance of understanding chemical processes in diverse environments. From the icy moons of our solar system to the distant exoplanets orbiting other stars, the interconnectedness of chemistry also has significant implications for addressing global challenges. Issues such as climate change, pollution, and resource depletion require a holistic understanding of chemical processes and their interactions with biological and environmental systems. For instance, the development of sustainable energy solutions, such as solar cells and biofuels, relies on advancements in chemistry and material science. By recognizing the interconnected nature of these challenges, scientists and policymakers can work together to develop integrated approaches that promote sustainability and protect the planet. Education plays a crucial role in fostering an appreciation for the interconnectedness of chemistry. By emphasizing the relationships between different branches of chemistry and their applications in real-world contexts, educators can inspire students to think critically and creatively about scientific problems. Interdisciplinary approaches that combine chemistry with biology, physics, and environmental science can provide students with a more comprehensive understanding of the complexities of the natural world. In conclusion, the interconnectedness of chemistry is a fundamental aspect of understanding the natural world. From the microscopic interactions of atoms and molecules to the cosmic processes that shape the universe, chemistry operates as a unified discipline that transcends traditional boundaries. The principles of chemistry are woven into the fabric of biological systems, environmental processes, and technological advancements, illustrating the profound connections that exist within the scientific landscape. As we continue to explore the intricacies of chemistry, recognizing its interconnectedness will be essential for addressing the challenges of the future and advancing our understanding of the universe. The journey through the interconnected realms of chemistry is not only a scientific endeavor, but also a celebration of the unity and complexity of the natural world. Chemistry is often regarded as a rigorous science grounded in equations and laboratory experiments, also possesses a profound beauty that resonates deeply with the human experience. It is a discipline that reveals the intricate dance of atoms and molecules, the elegant transformations of matter, and the delicate balance of nature. The poetry of chemistry lies not only in its scientific principles, but also in its ability to inspire wonder and appreciation for the world around us. At its core, chemistry is the study of matter and the changes it undergoes. This exploration begins with the simplest of elements, each with its own unique properties and characteristics. Hydrogen, the lightest and most abundant element in the universe, serves as the building block for countless compounds. Its ability to bond with other elements creates a vast array of substances, from water to organic molecules. The beauty of chemistry is evident in the way these elements come together, forming intricate structures that define the physical world. Consider the elegance of water, a compound composed of 2 hydrogen atoms and 1 oxygen atom. Water is not just a simple molecule. It is the essence of life itself. Its unique properties, such as its high heat capacity, surface tension, and solvent capabilities, make it indispensable for all living organisms. The way water molecules interact with one another, forming hydrogen bonds, creates a dynamic and ever-changing landscape. This molecular dance is a testament to the beauty of chemistry, as it underpins the processes that sustain life on Earth. The poetry of chemistry extends beyond individual molecules to the complex interactions that occur in biological systems. Biochemistry, the study of chemical processes within living organisms, reveals the intricate networks of reactions that govern life. Enzymes, the catalysts of biological reactions, exemplify this beauty. Their highly specific structures allow them to facilitate reactions with remarkable efficiency, transforming substrates into products with precision. The elegance of enzyme action is a reminder of the intricate design inherent in nature, where even the smallest molecular interactions can have profound effects on the larger system. In addition to its role in sustaining life, chemistry also plays a crucial part in the natural world, shaping the landscapes and ecosystems we inhabit. The processes of weathering, erosion, and sedimentation are all driven by chemical reactions that break down rocks and minerals, transforming them into soil and nutrients. The colors of autumn leaves, the vibrant hues of flowers, and the iridescence of a soap bubble are all manifestations of chemical interactions at play. The beauty of chemistry is woven into the very fabric of our environment, inviting us to appreciate the wonders of nature. The interconnectedness of chemistry and art is another dimension of its poetic nature. Artists and chemists alike explore the properties of materials to create beauty. The vibrant pigments used in paintings, the delicate glazes on ceramics, and the intricate patterns in textiles all stem from chemical processes. The chemistry of color, for instance, reveals how different wavelengths of light interact with various substances, producing the rich palette that artists use to express their creativity. This intersection of science and art highlights the aesthetic dimensions of chemistry, reminding us that beauty can be found in the most unexpected places. Moreover, the exploration of chemistry extends to the cosmos, where the elements forged in the hearts of stars give rise to the universe's diversity. The synthesis of elements through stellar processes is a cosmic ballet, where hydrogen fuses into helium and heavier elements are created in the explosive deaths of stars. Atoms that make up our bodies were once part of ancient stars, connecting us to the universe in a profound way. This cosmic perspective adds a layer of wonder to chemistry, as it reveals the shared origins of all matter and the intricate relationships that bind us to the cosmos. The beauty of chemistry is also reflected in its role in addressing global challenges. Development of sustainable materials, renewable energy sources, and innovative pharmaceuticals all stem from a deep understanding of chemical principles. Chemists are at the forefront of finding solutions to pressing issues such as climate change, pollution, and public health. The pursuit of knowledge in chemistry is not merely an academic endeavor. It is a quest to improve the human condition and protect the planet. This commitment to using chemistry for the greater good embodies the poetic spirit of the discipline, as it seeks to harmonize scientific inquiry with ethical responsibility. As we reflect on the poetry of chemistry, it is essential to recognize its impact on our daily lives. The food we eat, the medicines we take, and the materials we use are all products of chemical processes. The flavors and aromas of our favorite dishes arise from complex chemical reactions that occur during cooking. The effectiveness of medications relies on the precise interactions between molecules in our bodies. Chemistry is not an abstract concept confined to laboratories. It is a living, breathing part of our existence and education. Fostering an appreciation for the beauty of chemistry can inspire the next generation of scientists and thinkers. By emphasizing the connections between chemistry and everyday life, educators can ignite curiosity and wonder in students. Engaging experiments, real-world applications, and interdisciplinary approaches can help students see chemistry as a vibrant and dynamic field, rather than a collection of formulas and reactions. Encouraging creativity and exploration within the realm of chemistry can lead to innovative ideas and solutions that benefit society. In conclusion, the poetry of chemistry is a celebration of the beauty and wonder inherent in the study of matter and its transformations, from the microscopic interactions of atoms to the cosmic processes that shape the universe. Chemistry reveals the intricate connections that define our world. It is a discipline that inspires awe, invites creativity, and challenges us to explore the unknown as we continue to unravel the mysteries of chemistry. Let us embrace its poetic nature and recognize its profound impact on our lives and the universe. The beauty of chemistry is not just in its scientific principles, but in its ability to connect us to the world around us and to each other, reminding us that we are all part of a grand and intricate tapestry of existence. In conclusion, the exploration of chemistry reveals a rich tapestry of interconnectedness that spans from the microscopic interactions of atoms to the vast cosmic processes that govern the universe. Chemistry is not merely a collection of facts and formulas. It is a dynamic, an evolving discipline that embodies the beauty and complexity of the natural world. Through the lens of chemistry, we gain insights into the fundamental principles that sustain life, shape our environment, and connect us to the cosmos. The poetry of chemistry lies in its ability to inspire wonder and appreciation for the intricate relationships that define our existence. From the life-sustaining properties of water to the vibrant colors of nature and the elements forged in the hearts of stars, chemistry is woven into the very fabric of our lives. It serves as a bridge between science and art, revealing the aesthetic dimensions of materials and the creative potential of chemical processes. As we face the challenges of the future, the role of chemistry becomes increasingly vital. The pursuit of sustainable solutions, innovative technologies, and a deeper understanding of our environment relies on the principles of chemistry. By embracing the interconnectedness of this discipline, we can work towards a more sustainable and harmonious world, where scientific inquiry aligns with ethical responsibility. Ultimately, the study of chemistry invites us to reflect on our place in the universe and the shared origins of all matter. It encourages us to appreciate the beauty of the world around us and to recognize the profound connections that bind us, to each other and to the cosmos. As we continue to explore the wonders of chemistry, let us celebrate its poetic nature and the insights it offers into the intricate dance of life, matter, and the universe itself.